Hi everyone, welcome to the second international workshop on data simulation for decision making. My name is Elias Niño. I will be one of the chairs of this conference. So let me share with you some slides for guidance. Okay, so this conference and this workshop is thanks to some organizations. So we have Universidad del Norte in Colombia. We have MinCiencias in Colombia as well, Universidad de AFIT, El Applied Math and Computer Science Lab from Universidad del Norte, and we have the Air Force from Colombia. So basically we have this workshop. So the main point is data simulation, where we basically combine imperfect numerical forecasts with really noisy observations. And we have some hot topics which are tendencies in many aspects of data simulation nowadays. So we have background. We have also adjoint-free 4D bar-based methods, optimization methods for nonlinear data simulation, and non-Gaussian data simulation methods. So we have like optimization methods as well, or maybe we can have some sampling methods. And recently, people is just taking into account data-driven methods, in which basically what they do is that they incorporate some information from observations to build models, which basically mimics the behavior or the actual dynamic of the system. However, this is an ongoing work in progress, and many things need to be addressed before we can just take all these, for instance, machine learning methods into operational context. So there are many things to do before. So the conference, this is a 2-day conference, this workshop. So we have keynotes from different institutions. We have Adrian Sandu from Virginia Tech, United States. We have also Jeffrey Anderson from UCAR, University Corporation for Atmospheric Research, USA. We have Gary Vincent from Norway, and Arnold Hemming from Technical University Delft, Technology, the Netherlands. So these are our keynotes this year. Monday, so today, this is the schedule. So basically we have, we start with Jeffrey Anderson from UCAR. The talk is non-Gaussian, non-linear extension for ensemble filter data simulation. Afterwards, 9:40, we will have the talk on international initiative of predicting the SARS-CoV-2 pandemic using ensemble data simulation on Gary Vincent from Norway. Then we will have adjoint-free 4D bar for Arnold Hemming to Delft, the Netherlands, 10:40. An efficient ensemble-based methods for sequential data simulation at 11:40. So this will be my talk. And we will have the poster session at noon, where basically students will have like 10 minutes to present their posters. So it's only like 4 posters in this workshop. And then you can ask questions through YouTube channels. Also, the poster will be available through the workshop website. Tuesday, so tomorrow, October 27th, we will have Bayesian estimation and artificial intelligence as the source of uncertainties reduction for decision making. This will be given by Olga Quintero, Universidad de AFIT, Colombia. It's 8:40 a.m. Afterwards, we will have multi-fidelity ensemble common filtering with reduced order control variates. Here we have the participation of Andrei Popov, Chango Mo, Traian Iliescu, Adrian Sandu, all of them from Virginia Tech. Radar data simulation effects on decision making for operational WRF model for the Colombian Air Force. We will have Cáceres Richard from the Colombian Air Force. 10:30 will be the schedule. Then we will have a systematic evaluation of the operational 3D wire WRF model in Colombia Air Force. Soto Chicaeme from Air Force Colombia as well, and Andres Yarce from Delft. And robust shrinked ensemble common filter for state estimation, Santiago Lopez from Delft, Universidad de AFIT. And then we will have the closing remarks from this workshop. So let me introduce you to Olga, who is the chair of the conference. So Olga is full professor in Universidad AFIT in Medellin, Colombia. So Olga, welcome to the conference, and again, thank you very much for your support and making this workshop a reality.
Thanks, Elias. Welcome, everyone. I would like to stand this start of this workshop. I'm very happy and very glad to be the chairwoman today. Thanks for everyone. We are supposed to having this workshop in Barranquilla. Nowadays, we are back home. And I know that it's not necessarily easy for all of us coming from Europe. We have a different time zone. The same here in Colombia. So this year is going to be held on YouTube, and we're going to use StreamYard. From my point of view, this workshop is a milestone for Colombia as well as for Latin America. Elias and me, we have been working so hard on trying to establish the field of data assimilation or Bayesian estimation for large-scale models. But something that is really special about this is that we managed to get together worldwide experts on the field, and we managed also to involve our PhD students and several researchers from Colombia. And this is the result of a very, very long way from individual research and getting together a team of incredible people. Thanks for joining us. And I feel that this workshop is going to be the result also of a huge network of collaboration. I will establish the dynamic of this session for today. I'll be sharing, and I have two computers. I'm going to be monitoring the YouTube channel. Just in case you have questions, please feel free to sign in to YouTube channel and write down your questions. I'll be directing your questions to the speakers. If you want to engage a long conversation, because of already Professor Sandu asked me about how to establish a two-way communication, I'll be very happy to provide you the link to join the StreamYard. And please just write down your questions. Feel free if you are a PhD student, if you're a master's student, if you are a researcher, or if you are just part of the public, no technical public, but you are interested in to join our event, just feel free to do it. Okay, I am very happy to introduce Jeffrey Anderson, and this is a very special talk because we as Colombians are not necessarily aware of how complex is our atmosphere. And as part of the Universidad AFIT Mathematical Sciences Department, and also a researcher and part of the Colombian Air Force as an officer, we understand the complexities of our country and our atmosphere for decision making. But our field is not necessarily easy, speaking from the complexities of the nonlinear and no-Gaussian dynamics for not only the weather, but also the chemistry and transport dynamics for pollution. I will mention a program that is now being in progress. Is called Exposure to Pollutants Regional Research, and Uninorte, Universidad de AFIT, Universidad CES, Universidad de Antioquia, we are working together to try to determine not only the weather dynamics, but also the chemical transport dynamics, but also the effect on the humans and the health of some ecosystems. And this is a challenge, and I will be very happy to have Jeffrey Anderson speaking about the fundamentals of data assimilation and the new progress in research, and trying to get the entire scope for our students and for the practitioners about the need for incorporate observations into our models in order to forecast. So welcome, Jeffrey Anderson, to our workshop, and we are very happy to have you here.
Thanks, Lucia, and thanks to all the organizers for inviting me. It is about -12 here in Colorado this morning and snowing. It's also still dark, but so I think it's a little bit different than what it is in Colombia. I think I'd rather be in Colombia. Lucia, can you go ahead and share the slides? I'm not seeing them yet. Okay, and go ahead when you can and get those full screen. So I'm mostly going to be talking to the students today. A lot of the invited speakers have seen most of this work before. My apologies to you. But for the students, I'm going to show you that there are a variety of different ways one can try to do research and apply new methods on data assimilation. And you'll see that in my presentation, there will be exactly one equation. I think some of the later presentations today, there will be many, many times that. There's some excellent mathematicians here. And I'm not an excellent mathematician, but I can still do useful, I hope, research on new features of data assimilation. Next slide, please. So I'm going to start by showing you just a schematic overview of how I think about ensemble data assimilation. So in this cartoon, down in the lower left, there is 3 blue asterisks. And each one of those represents the entire state vector, all the numbers that describe, for instance, an atmospheric model. So there might be millions or even billions of numbers in each one of those asterisks in a modern model. And in this sequential way of showing how ensemble data assimilation works, the first step is to make a forecast from the analysis, the best guess at the previous time t sub k, to the next time at which we're going to use observations to update our estimate at t sub k plus 1. And so that's the green vectors. Next. The second step is we can realize that, let's see, I'm not sure if you heard to go to the next slide. We can realize that we can use the observations one at a time, even if we have many, many observations of the atmosphere at approximately the same time. We can use them one at a time without loss of generality if we ignore correlated error on the observations. And I'm going to do that today, but it's a big and non-trivial research problem. So these H's here are forward operators. They're a function that applies to the state of the model and creates an estimate of what the instrument will see. So in the top panel here, this is in what we would call observation space. So I have 3 estimates from my forecast ensemble in green of the observation. And then I have what the instrument actually observed is a red dash. And I also have the error distribution from the instrument in red. Next slide. So I can do a scalar problem here in observation space where I apply some method, for instance, the classical ensemble Kalman filters or a deterministic ensemble Kalman filter. I can apply some method to combine the information from my green prior values, the 3 of them, with the observed stuff in red. And I can get updated estimates of the state of the observed variable. And those are the blue values. And the increments between the prior estimate of the observed value and the posterior or data assimilation updated values are the blue vectors. And I can do that in a Gaussian way, but I can also do this one-dimensional update in a non-Gaussian way, and I'll talk about that in a minute or two. Ensemble Kalman filter classical methods assume Gaussian, and thanks for advancing. So the next step then is to take those increments for the observation, and I want this observation to impact all of the model state variables. And again, this classical way to do that is to simply do a bivariate regression problem where I regress those increments onto each state variable independently using the prior ensemble bivariate statistics. And again, theory tells me that I can do this problem independently if I'm just implementing a Kalman filter type algorithm. Okay, and so I would then go ahead and repeat this process over and over again for each observation that was available. So I would compute the forward operators, get the increments, and regress those onto the state variables. I just do that over and over again until I've used all the observations. And when that's done, then I just repeat the whole process. I do a forecast to the next time, tk plus 2, and do it over again. Next slide, please. So I'm going to talk for a minute now about the underlying stuff. This is the only equation I'm going to show, which is a representation of Bayes' rule. And I'm just doing this in one dimension for now. So this is, for instance, how one could most generally think about that problem in observation space from the previous cartoon of slides. So here I've shown in green a prior distribution from the forecast model, and it's non-Gaussian. It could be arbitrary. And right now I haven't shown anything about how I would get that from an ensemble. I just have it from somewhere. And Bayes tells me that I take that prior information, and I also take, next slide please, information from the observing system, which is called the likelihood. So that's the probability I would have observed the thing that I did observe, y. So for instance, I would have observed a particular temperature outside my window this morning, given a particular value of the state. So I now have the prior in green, the likelihood in red, and Bayes tells me that I need to take the product of those two, and that's a pointwise product. So for instance, at the value of temperature equals 2, I would multiply the green value times the red value, and that gives me the blue dashed value. And then the final step is I need to normalize those. So I compute the area underneath that product curve down at the bottom because I need the final answer, the probability, the posterior probability shown in blue on the left of the equation, to be a probability distribution. So I need the area under that to be 1, and I get that by dividing by a normalization that's the area under the blue dashed curve. And so my posterior there, or analysis as it's often called in atmospheric applications, is the blue probability distribution that has combined the information from both the prior model forecasts and the information from an observation, the likelihood. So what I've shown here is a completely nonlinear representation, but in fact, normally for ensemble common filters, we assume some sort of Gaussian form for that. And so the slide that's up now shows I've replaced these probability distributions with some Gaussian approximations. So I've assumed that the prior is Gaussian in green, that the likelihood is Gaussian in red, and that the posterior is Gaussian. And in fact, because of the fact that a Gaussian times a Gaussian gives you a Gaussian, that happens automatically once you assume that the prior and likelihood are that way. If you could go to the next slide now. So for quantities like temperature, it makes often good sense, and it often works very well to use a Gaussian approximation. And so there's been great success with using ensemble common filters for all types of applications. So what we're talking about today is looking for non-Gaussian. We need to go back one slide, please, Lucia. So we're talking about non-Gaussian and nonlinear extensions to ensemble common filters. And it's important to understand that these are extensions. These are methods that improve something that's already working pretty well. It's difficult to improve on common filters for most applications. And so we'll be looking for opportunities to improve where the problem is particularly challenging for linear and Gaussian cases. One possible example, and my red stippling is not showing up very well on the broadcast here, but instead of a temperature, suppose we're really trying to do an air pollution application. And so we're interested in the concentration of some atmospheric tracer, maybe ground level ozone. So a concentration is a bounded quantity. It can't be negative. And so we don't want to have, if we can avoid it, probabilities saying that the quantity can be negative. And very often, of course, since a Gaussian is non-bounded, any application where we fit a Gaussian and use that as our prior probability or our likelihood is going to end up giving us some non-zero probability of a negative concentration. Again, people have done pretty well allowing that to happen and fixing it up after the fact. So just making negatives positive, for instance, in a lot of applications. But there is evidence that, as an example, tracer applications like this are a place where getting rid of these assumptions about Gaussianity can be helpful. So Gaussianity can definitely be a poor choice in some applications like this. Next slide, please. So I'm going to start out talking about, again, just the one-dimensional problem here. And so back to the original cartoon I showed, talked about using each observation in turn, and one of the steps was to compute a posterior and associated increments for the ensemble estimate of the observation. And for the next 5 to 10 minutes, I'm just going to be talking about that observation space problem. So in the bottom of this slide, I have 5 ensemble members. And again, these examples, for most methods and applications, we need many more ensemble members than 5, or 3, which I showed in the earlier cartoons. But it's easier to visualize these things with small ensemble sizes for these examples. And again, for the students, one of the things you're going to see here, this work was originally done more than a decade ago. And the way that I do research on data assimilation is a very intuitive process. So I try to understand the equations that we have, and I try to understand the problem. But then very often I'll work on methodologies that are driven by intuition and my understanding of what's going on rather than a mathematical derivation. People have made great contributions to the field by working directly from mathematical derivations and deriving new equations, and that's not how I work. So I'll continue describing this method in just a second, but in general, I developed this method. I tested it in many applications and figured out how it worked. And then I collaborated with applied mathematicians who actually did the mathematical work and derived something about how the equations are related to the problem we want to solve. And so this is definitely another way that you can work on ensemble data assimilation besides just driving it directly with mathematics. So back to this slide then. I have 5 ensemble members, and Lucia's gotten just a little bit ahead of me. If you can go back one slide. And so I'm going to somehow try to get myself a continuous representation of the prior probability from these 5 ensemble members, but I want that continuous representation to allow non-Gaussian behavior. If I were just doing a classical ensemble common filter, there's a variety of classical ensemble common filters, what I would do is compute the mean and the standard deviation of these 5 ensemble members and get a Gaussian distribution from that. Instead, I'm going to do something a little bit crazy. I'm going to base this work on ideas called a rank histogram. A rank histogram is a method for evaluating and validating ensemble forecasts, and it says that if the ensemble is really a random draw from the distribution that the truth is drawn from, then the probability that the truth lies between any of the ensemble members should be uniform. I won't go further into why that's the case today. It's something, if you think about it, if you haven't seen it before, is fairly intuitive, and I would be happy to talk afterwards. So following that, what I'm going to do is I'm going to create a continuous probability distribution by saying that 1/6 of the probability lies in each of the regions that this ensemble puts the real line into. So those 5 ensemble members at the bottom, there's 4 regions in between them and then 2 regions on the tail, a total of 6, or n+1. And I'm just going to put 1/6 of the probability in each one of those. And Lucia, now you can go ahead until you see the Gaussian ones on the tail. So that's 3 or 4 slides ahead. Okay, so in each case here, stop there. I'm putting 1/6 of the probability into each one of these things that I'll call bins. And so you can see the probability is higher in the ones that are closer together. So for instance, the space between the 2nd and 3rd ensemble members is higher than the space between the 4th and 5th ensemble members. But the total probability in there, the area of the rectangle, is the same in each case. And then on the tails, I've put a Gaussian distribution. I don't know quite what else to do on the tails, although I'll talk about that more later. But anyway, this is one idealized way of trying to represent a continuous probability, which is now shown by the green area up above for this problem. So remember that Bayes' formula told me that I also need the likelihood, and we're good on this slide, let's say. So in this particular case, again, I'm working for the observed variable. Very often observed variables come with normal Gaussian distributed likelihoods, and that's what I've shown with the red curve here. But the bottom line is, whatever the shape of the likelihood, I can compute the value of the likelihood for each of the ensemble members, and that's what's shown in the red asterisk. So now I have a continuous likelihood, the red curve, and a continuous prior, the green. Next slide, please. For computational simplicity in this particular method, which is called a rank histogram filter, I'm going to change the representation of the likelihood to simply linear, so a linear approximation for now between each of the asterisks, and I'm leaving it Gaussian on the tail. And so now Bayes tells me, as you recall, that I have to take the product of the green prior and the red likelihood, so I'll go ahead and do that on the next slide. I get this funny looking continuous. Keep going until the blues are all there, so 4 slides, Lucia. So in each one of the bins, I get a rhombus type shape, and on the tails, I get a product of Gaussians, which is Gaussian. And stop there, that's good. So now I have a continuous, a rather weird representation of the continuous posterior in the blue lines. And I need to go back and get a continuous representation of an ensemble because I need the ensembles to make a forecast eventually. And so the way I'm going to get my posterior ensemble, which is shown as the blue asterisks above the green priors, is I'm simply going to pick them so that they partition the blue posterior curve, piecewise continuous curve, in the same way. So the first blue asterisk, which is about minus 0.75, 1/6 of the area under the whole blue curve lies to the left of that asterisk. The next blue asterisk, about minus 0.25, 1/6 of the area under the blue curve lies between the first ensemble member and that second one, and so on. So those 5 blue asterisks for the posterior partition in the same way that the green asterisks partitioned the prior. Next slide, please. And the next slide shows what I would have gotten if I'd used a traditional ensemble Kalman filter, in this case something called an ensemble adjustment Kalman filter, which is an exact deterministic representation of the Kalman filter itself. And so if you compare the 2 rows of blue posterior asterisks, they're very similar in this case. So it was a nearly Gaussian problem in some sense, and so I got about the same answer. Next slide, please. On the other hand, if I'd applied this to a distribution that was distinctly non-Gaussian, for instance, here the prior shown by the asterisks has one extreme outlier at minus 2.5. Then when I apply the rank histogram filter, which is the top row of blue asterisks, I get a posterior that eliminates the outlier, which is inconsistent with the likelihood. But the EAKF, which assumed Gaussians, leaves the outlier out about minus 1.7 in a place where really there was no evidence that there was particular probability density in the prior. And so in this case, which is non-Gaussian, things work very differently. So this is an example that at least this method is doing something that the Gaussian methods don't. Whether it's doing something useful or not, what has to be evaluated. Lucia, can you skip 2 slides now, please? So now I'm going to go on and talk about why tracers can also lead to nonlinear relationships between an observation and a state variable. So I've talked about how they can be non-Gaussian. Now there's that second part of the problem in the cartoon where I want to relate an observation to a state variable. So if we hold on for a second here on this slide, I have a posterior distribution in an idealized one-dimensional case. So the horizontal axis is longitude, and I've plotted a black curve. I have a blob of tracer shown in black, and maybe I know the position of that blob fairly well, so there's not much uncertainty. But because I'm doing a data assimilation problem, I may have quite a bit of uncertainty in my prior wins. And so I'm going to use those different ensemble uncertainties to advect that posterior blob forward in time. I'm going to make a forecast of where the blob is to a time when I have observations. So the light blue shows one possible ensemble member of the wind, and it shows where it moves the prior in light blue. Let's see the next slide. And if I have an observation at longitude 1.1 of that tracer concentration, that's marked in the green asterisk, so that's my observation prior for this ensemble member. Then for my bivariate ensemble update, I'm going to take the wind value of 1.2 and the concentration value shown by the green asterisk. Next slide, please. And I'll put them on a bivariate distribution, which has concentration on the horizontal axis and velocity on the vertical axis. Okay, next slide, please. Okay, but as I said, I have some uncertainty. So maybe one of my other members, ensemble members, says that the wind is really 2. And so that's shown in magenta here. And so again, that advects the tracer blob a lot further in this case. And coincidentally, in this case, it gives exactly the same value for the observation at longitude 1.1. And so again, I plot the bivariate values of wind value 2, tracer concentration 1.1. And let's see, that's good. You can step ahead through this until we see a whole bunch of green asterisks in the lower right panel. So each different ensemble member has a different wind, and stop there. And so if I had a whole bunch of these winds, I would end up getting a relationship in the lower right plot between concentration and wind that is highly nonlinear here. So a linear approximation could work, but it could also be very poor. Again, this is an example why if you're working on concentration problems for, say, air pollution, there may be opportunities to look at nonlinear methods to also improve things. Okay, next slide, please. So, it's important not to get confused about what I'm going to do next. In the previous set of slides where I developed the rank histogram filter, I was talking about the rank histogram filter as a way to do a non-Gaussian distribution for the observation prior. That was a scalar problem. Now I'm going to extend that methodology, and instead of using it to get the posterior for an observation, for an observed variable, say the temperature outside, I'm going to use almost the same methodology to directly update a model state variable. And so this plot looks very much like one of the plots I showed before, but now the horizontal axis is not for the prior estimate of an observed variable. It's for the prior estimate of a model state variable. As an example, maybe temperature at a grid point in the model. And I'm going to do exactly the same thing I did before. Since I have ensemble forecasts, I have a prior estimate of this state variable. And so that's the 5 asterisks again. And I'm going to do exactly the same procedure to get a continuous estimate. So that's taking 1/6 of the probability and putting it between each one of the ensemble members. Next slide, please. Similarly, I have a value of the likelihood for each ensemble member. But the important distinction now is I'm not working with an observed variable. And so even if that likelihood is Gaussian, here I would compute the value of the likelihood for each observed ensemble member. Those aren't plotted here. And then that value is associated with the ensemble. And so the likelihoods are no longer have some nice functional form for this problem. I have a likelihood for each ensemble member as shown. In the next slide, I can go ahead and do what I did before. I can fit a linear interpolation between each one of the likelihood values. And now on the tails, I no longer have some nice Gaussian on the tails because, again, this is for a state variable. And so I don't even know what the form of the likelihood is here. And so since I don't know anything else, I can just put a linear value out there. That linear value is half of the value of the last likelihood that I have. By doing that, I again have a continuous prior in green and a continuous likelihood in red. On the next slide, I can do what I did before. Bayes tells me to take the product, and so I get a continuous blue posterior. And then on the next slide, I again find posterior ensemble members by putting 1/6 of that posterior continuous distribution in each one of the intervals. And so now I have gone directly to a posterior representation for the state variable. That's the top 5 blue asterisks. And I can compare that again to what I would have gotten if I'd just done a Gaussian assumption with a linear regression. Okay, so that's the bottom row of blue asterisks. Next slide, Lucia. So now I can build a cartoon that looks like the following. I again do my forecast like I did before. Next slide. I compute the forward observation for an observation again. That's to get the likelihood values. Okay, they're shown. Continue to step 4, please, Lucia. Next slide. But now instead of doing a linear regression, I don't have to do that. I can just compute the increments directly by the method I just showed. And next slide. And so now I can get these. There is a technicality, and given the way time's going, I'm not going to discuss that technicality in great detail here. And that is that the way that the values are associated with the ensemble members is technically kind of arbitrary here. And to make this algorithm work, one has to think very carefully about that detail. And again, especially for students, it's probably not time for you to catch that level of detail yet. I have a paper and would be happy to talk. Next slide. And so I can update all the state variables, and then I'm ready to move forward in time. Skip 2 slides, please, Lucia. One more. And one more after this, I think. Okay, so I'm going to quickly show some examples to demonstrate that this method has some validity. I'm going to apply it to an idealized problem where I just make a random draw from a bivariate Gaussian distribution. And I say one of those variables is observed and the other one isn't. And then I'm going to simulate observations. And I'm going to look at the posterior statistics to see how this new method does. Next slide, please. And so this slide shows the results for a bunch of different correlations. So each correlation is a different type of sample problem. These solid lines are the value of the root mean square error. So it says how well this method's doing for different ensemble sizes. And the dashed lines are for the classical Gaussian ensemble adjustment Kalman filter. And what one finds, which is not a surprise, this is a Gaussian problem by design, is that the new method has generally significantly larger errors than the classical method. And let's see, I'd actually, given the time again, like to skip forward quite a ways now. So keep going. Okay, one more. And actually, even one more. Sorry, having you drive here was unfortunate. So one can compare these different methods, as I said, and what you find is that the new one is as good. Keep going. But you can see the qualitative differences here now for various non-Gaussian problems. And on these slides, I want you to just pay attention to the bivariate distribution at the left. The green asterisks show the prior. The blue asterisks show the posterior. So this is an example for a bimodal distribution, and this is using an EAKF, and it ends up putting a lot of posterior in the middle where there's no prior. Next, please. If you apply the observation space rank histogram filter, it gets rid of most of that problem. Next slide, please. And this fully bivariate nonlinear non-Gaussian method, the MARHF, here, it also does the same thing. So it moves almost everything to one of the prior places. So this looks much more consistent. Next slide, please. Okay, so this is an example with a single prior outlier. So there's one green asterisk up on the upper right. If I use an EAKF, a classical Gaussian method, it's not able to get rid of that. Keep going. If I use a rank histogram filter, a little bit better, but still not good. And if I use this fully nonlinear non-Gaussian method, the next one, you can see it does a better job on eliminating the outlier, but still doesn't get rid of it. So next slide. Okay, so this is an example of that cosine form that one gets with advecting a tracer. So here the EAKF, the classical Gaussian method, does something not very good at all. Almost all of the posterior moves away from where the prior is. Next slide. And the observation space, which only takes account of the non-Gaussianity, does much the same thing. But next slide. The nonlinear non-Gaussian method does a pretty good job in eliminating all of it. So it is able to realize that there is a back one still, Lucia. So you can see that the blue posterior has picked out two areas of the green prior curve. So it says basically that the wind is either fairly light or the wind is fairly strong. And that was consistent with that example where I showed earlier that two different winds can still end up having the same concentration value, but are related to very different overall tracer distributions. Okay, I want to skip ahead away, Lucia. So let's go 3 slides. So go past the things that look like this. And this is just showing an example now in a cycling data assimilation for Lorenz 63. So that's a 3-variable model I think most of you are familiar with. If you go to the next slide. And so this shows an example of a fairly infrequent observing system for the Lorenz 63. And each one of these panels is the prior and posterior distributions of the x and z variables. The priors are all the same, shown in green. And the posteriors are shown in blue. The top 2 methods are, the upper left is a classical Gaussian linear filter. The upper right is the rank histogram filter, which is non-Gaussian but still linear. And the bottom 2 are variants of this nonlinear, non-Gaussian filter. And again, one would like to see the posterior asterisk in blue lying somewhere close to the model attractor, which is highlighted by the green prior here. And you can see that the non-Gaussian, non-linear methods do a little bit better. Let's skip ahead a good ways now, Lucia. So keep going until I want to skip over the Lorenz 96 test given the time. And so there's around 10 slides where we'll start seeing plots of results. So go through all the bar plots and stop when we're past the bar plots. Okay, so there are additional things one can do because these methods I've been describing allow you to enforce additional constraints on your priors, and they allow you to do absolutely anything for the likelihood. So the likelihood does not have to have a convenient functional form. And so let's demonstrate that again, starting out with just again a picture of one of these priors from the rank histogram filter. So this particular figure again is showing that I have fitted a prior distribution in green, and it is unbounded because the tails have Gaussian forms. If you go down one slide, so let's suppose that instead I'm actually working with a variable, so a state variable that is the concentration of ozone at a grid point. And so we know that the prior should not go below 0. And so it is easy to adjust this method of creating the continuous prior. Instead of having a Gaussian tail below the lowest ensemble member, which is at about 0.4, I can instead switch and say, I'm just going to have a uniform blob of prior probability below that lowest ensemble member, but it's bounded at 0. Okay, so that is a trivial modification to this. And so now I get a continuous prior probability that is shown in the green here. Can you go back up one slide, Lucia? So when I had the continuous tail on this distribution, it allowed the posterior, the blue solid curve, to have negative values. And when I did the resampling to get the blue posterior ensemble, the smallest ensemble member had a value of minus 0.2, which is against the rules. Concentration can't be negative. Go down again one slide. When I switch to the bounded prior, so that the prior stops, the posterior also stops there, and the lowest ensemble member actually has a positive value now of about 0.3, which is consistent with the bound. So I can apply bounded quantities very easily. I can apply double bounded quantities. If I have other constraints on the prior, I can apply them in this methodology. Down one, Lucia. Okay, so what I'm going to do now is run, again, a bivariate example, highly idealized problem. My prior, I have 2 variables, one observed and one unobserved. And they are, that bivariate distribution is drawn so that their logs are bivariate Gaussian. So if the log of the distributions is Gaussian, that means that their prior, I exponentiate their distribution, so the prior is non-negative. So these are bounded quantities. They cannot be negative. One of the variables is observed, and instead of using a Gaussian likelihood on the observation, so instead of saying that the observation is plus or minus 2 as a standard deviation, I'm also going to use a likelihood that is positive definite. So in this case, I will say that the instrument has a likelihood that is a gamma, and I'll pick a particular shape parameter. So gammas have 2 parameters that define the distribution. The shape parameter will be chosen from one of the ensemble members and a scale parameter of 1. And I'm going to assimilate a whole bunch of observations of one of the state variables, okay, from different random draws. Next slide, please. And this slide actually shows, for those of you who haven't worked with gamma distributions recently, an example of gamma distributions in solid red. So those are the likelihoods that are actually associated with these instruments. One can fit a Gaussian to a gamma, and so if when we're trying to do a Gaussian data assimilation, you might use the red dashed values of the distribution. And so those would be an approximation. So the correct thing is to use the gammas. Next slide, please. So I'm going to use 5 different assimilation methods on this highly idealized problem of a pair of bounded quantities. In the first one, I'm just going to use a classical ensemble Kalman filter, the ensemble adjustment Kalman filter, which assumes Gaussianity and linearity. I will try 4 other filters for which the observed variable will be treated in a non-Gaussian fashion using the rank histogram filter. And for the unobserved variables, I will try either still using linear regression in 2 cases, or going ahead and using this method that avoids the linear regression and allows nonlinearity. Okay, so the method is called the marginal adjustment rank histogram filter, shown in blue. And finally, in the first 3 cases, I will use a Gaussian likelihood, and in the last 2, I will go ahead and use the actual gamma likelihood. And good, you can go ahead and advance, that's good. So the plots on the next slide show the results for the 5 different methods are in different curves. Each one shows, each of the 4 plots is for a different ensemble size, from 40 up to a ridiculously large 1280. If the curve is solid, a gamma likelihood was used, and if the curve is blue, it uses the fully nonlinear. So this first slide is actually showing how many of the ensemble members on average end up being negative. And remember, that's sort of wrong here since it's a bounded quantity. And if one uses the gamma likelihood and the non-Gaussian nonlinear method, none of them end up negative by construction. On the other hand, if you use one of the other methods, the number that are negative, the percent that are negative, basically is unchanged by increasing the ensemble size, and there's a significant number that end up being non-negative. Next slide, please. This slide shows the actual RMSE, and again, perhaps not surprisingly, in solid blue, the method that uses a nonlinear, non-Gaussian, and uses the gamma likelihood has the smallest RMSE by quite a bit in general. And the other methods become progressively worse, with the one that assumes all the standard things, the EAKF in black being the worst. One more slide, Lucia. This actually shows the errors in the variance. Okay, so I used a method, an exact method, a very expensive method to get the real answer. And again, the variance or uncertainty is better represented by the methods that are non-Gaussian, nonlinear, and use the gamma. And it looks like I'm about at the end of my time. Let's do one more results slide, Lucia. So one more. Okay, I actually took that one out. So very good. The summary of the science I showed you here is that one can come up with methods that still work in the ensemble context that allow a non-Gaussian representation of the prior. Okay, so for instance, the rank histogram filter that I showed in observation space. One can extend these methods to allow, and note I say limited nonlinearity. There's no doubt that there are plenty of nonlinear type things where this method still performs poorly, but there's a number of relevant types of nonlinearity where it performs better than standard ensemble filters. I gave examples of tracers here because they both generate nonlinear things and they tend to be bounded. And these methods definitely allow strong new ways to do bounded quantities. Now, as in all cases, there's a need for extra computation here, and so the nonlinear, non-Gaussian method is definitely more expensive than a standard filter, less than a factor of 2, but that means it has to work better than a classical filter that uses twice the ensemble size. And that means that it's not going to do better for problems that are almost Gaussian and almost linear. So one thing that you have to do is look for applications where maybe you can turn on these enhanced methods in cases that you know a priori to need nonlinear, non-Gaussian methods. So again, I want to close this again for the graduate students and maybe to give some context for where some of the other talks later on will be going. I don't think we actually have someone talking about particle filters in the meeting. I may be mistaken. But there's really general powerful methods. Peter Houtekamer perhaps has done the most on this. Really general ensemble type methods that can represent very general distributions and get the right answer. But they're extremely expensive. And then there's been work on these ensemble filters going on since the early 1990s. Garrett was the pioneer in all of that, so 25 years now. And those methods are not as powerful as the particle filters, but they're much more affordable. And so one of the big themes that's been going on for decades now is researchers on both sides of those methods trying to move towards a middle ground, either finding algorithms that have the power of particle filters but are cheaper, or ensemble methods that have more of the capability of particle filters while retaining their low cost. And this is one example of that sort of direction. There's also variational methods, which we'll see more about later in the meeting. And there's been enormous amounts of work about trying to take good parts of variational methods and combine them with certain parts of ensemble methods. Again, looking to get the good parts of the methods while avoiding some of the shortcomings. And those areas of research are really, really where good things are going on right now. The important part is that students need to master at least the basics of a couple different methods there and then look for the stuff in between. And that's always a place on any sort of research problem to look at mastering things that other people have developed but haven't looked at the space in between them. And I think I will stop there. I hope that some of this was understandable, especially for the students.
Can you hear me now?
I can hear you.
Okay. Well, I will ask you to turn on your camera, please, Elias.
We'll see if my bandwidth is going to support that.
Well, allow me to introduce your event. Thanks for joining us, Jeff Anderson, Elias Nino. We already have some questions in the YouTube channel, and I really would love to have you answer them because of what you already presented is really interesting for us. Welcome, Arnold Hemming. Now you are in our live broadcast workshop.
Hi, Arnold.
Okay, I have some questions for you. Randy escribe con suegra, Elias, student. He is asking you, how will it perform in highly multivariate or highly correlated cases?
Okay, so as far as highly multivariate cases, so I think what the questioner is asking here is if the Gaussian assumption is very poor in that there are significant values of higher order than bivariate statistics that are important, then the expectation is that the method would be challenged, because again, it is only looking at the bivariate statistics between the observation likelihood and the state variables. And so if there are meaningful third moment or higher correlations, those are going to be a challenge for this method. They will, of course, also be a challenge for any method except a pure particle filter, because if you're trying to do an optimization in a variational method in a context where third order moments are significant, that is going to be a very, very complex optimization. Similarly, highly correlated cases, again, I'm not quite sure if that's a reference to the observational error variance. Again, one would have to extend these methods, and that is possible. But the method as described here assumes uncorrelated observation error distributions. And so if there were highly correlated observation errors, you would have difficulties.
Okay.
Well, thank you. We already have another question for you from Andrei Popov. I assume that is from Virginia Tech. He's asking, is there a connection between your method of building this synthetic distribution and methods such as the principle of maximal entropy? Is this the ensemble analog?
Okay, so because I'm ignorant here, I will say that may be a good question. I do not know the answer to that question. And this is an example of what I was telling the graduate students before. My reply to you might be, I don't know, but maybe we should talk more about this. And that's a way to build really interesting collaborations. And so the answer is, I don't know if this is the principle of maximal entropy and this is the ensemble analog, but I would be quite interested in talking more about that.
Well, thank you. Elias, Gear, Arnold, do you have any questions for Jeff?
So I don't know, maybe Guy or Arnold have any question. I would like them to start.
Well, I do have an intervention regarding this method. I am the one who's working with particle filters here, and I really would love to know if you already have been thinking about how to extend this proposal to the particle filtering. I've been following the work of Jonathan Potterhoy regarding the particle filtering or the localization for the numerical weather forecast. And how do you think this will be pointed out for such an applications, taking into account that we already have a model operating here in Colombia for meteorology and the chemical transfer model? What would you like to tell to our students, or what will be the directions if we wanted to try to get your idea into the operational setup here in Colombia?
Okay, and so I'm not completely familiar, unfortunately, with the operational setup you have. I have worked, John, again, is an example of someone I've worked with who is mathematically more gifted than me. So John was actually my postdoc when he was developing the localized particle filters. That work is definitely an example of what I mentioned on my summary slide, is looking at areas between the ensemble Kalman filter and the particle filter. It was basically an attempt to allow the general representation of probability distributions of the particle filter while minimizing the number of particles required by applying a localization technique, which basically makes the problem, divides the problem into a whole bunch of smaller problems that can be solved simultaneously. The intersection between the work I'm proposing here and Potterjoy's is that Potterjoy's methodology can be expressed directly in this cartoon framework that I showed at the start of my talk. And in fact, he originally developed his methodology in our software system, the Data Assimilation Research Testbed. And so if you have Potterjoy developed in a context that looks something like that, it is definitely possible to consider, as an example, doing some things with the boundedness on the distributions that I'm showing. So Potter-Joy's method, while it represents, as all particle filters do, an arbitrary distribution, it does in fact struggle with boundedness and other things with small ensemble sizes. So it tends to bleed the distributions into negative values in those cases. And so there's probably some room to think about hybridizing some of the advantages of using the rank histogram with what Potter-Joy was doing. The exact details are unclear. It would certainly be a research problem, and John and I have discussed it a couple times without really starting on working on anything.
Well, thank you. I'll take some minutes in order to ask you to talk more about your test bed. Because for us, we've been working a lot with the data simulation implementations that we already have from ourselves from scratch. Would you like to tell us more about the DART test bed for data simulation in order to get the students involved with your own applications and how they can use it for learning and also to try to develop some of particularly and specific applications?
Sure, I'd actually love to do that. So, so my team here at the National Center for Atmospheric Research, so the National Center of Atmospheric Research is run by the University Corporation for Atmospheric Research. And one of the big parts of our mission is to support the research of faculty and students at more than 100 universities, mostly in the United States, but there are also member universities in other countries. And of course, we are very interested in supporting those students and faculty, but also in supporting users who need data assimilation capabilities at a variety of other places. So DART, the Data Assimilation Research Test Bed, is a community facility for ensemble data assimilation, education, and research. It is designed to work with very, very simple applications for students, and we include a large variety of interactive tutorial materials. There are a number of university faculty members around the world that teach with DART, a couple dozen going right now. At the same time, exactly the same code framework can be run with huge models on big supercomputing. So we have some operational weather prediction users. We have a lot of people doing research on any number of geophysical problems. In fact, we have a couple people doing research on epidemiology, which I think is relevant to the next talk coming up. It may or may not be great to use ensemble methods for those things. But basically, DART is designed to not only support education for graduate students, but also to allow them to have a framework in which they can develop ensemble data assimilation for new applications or try things. And Potter-Joy was an example. He started using DART as a graduate student and then continued into his postdoc and still uses it some at Maryland for his research today. We use it with a number of collaborators on big NCAR models. So it will run with, for instance, a 1/10 of a degree ocean model coupled to 1/4 of a degree atmosphere model. So that's more than 1 billion state variables on many tens of thousands of cores. Again, the goal has always been one of clarity and ease of use rather than absolutely being the most powerful, fastest operational data assimilation system. And it is limited to ensemble methods and their derivatives, so we've made no effort to do variational or variational hybrid approaches. Nevertheless, if you have students who are interested in doing this stuff, we do support it. You can get it, I think, if you put up my last slide one more time, there's a link there. But if you just search for NCAR DART or search for my name, you'll also find it. And I don't know if you're going to post the slides. It's also on my last slide, links for that. So basically, DART is what we do. Research like what I just showed you, we're doing that sort of research, exploring ways to make DART more powerful and more useful to a wider array of applications. This particular research approach is driven by the fact that we have a lot of people who want to do atmospheric chemistry where bounded quantities are really, really important.
Excellent. So, Jeff, yeah, I think we have a lot of students who are highly interested in working with your software package. I mean, it's very attractive, it's very intuitive also, the use, so, and it can be extrapolated to very highly complex physics. So, Jeff, I have a question with regard to the recent methods, right? So basically you target each state variable, then you construct the histogram, and then you adjust the components with the observation that you have, right? So it's basically an extension to the sample adjustment Kalman filter to incorporate information based on non-Gaussian distribution, non-Gaussian assumption. So, you know, once I tried to do something similar, but the problem in that moment was how I force continuous dynamics in the wall domain, right? Because I'm separate and start like adjusting each component with regard to the observation of any rule. I don't know, maybe the nearest observation or maybe some sort of the correlation function. But how can we ensure to have a consistent flux in the entire domain, right? As if we try to do something in a very single shot, making use of all observation and all state variables, how we can enforce that? I mean, I'm guessing that we can impose some sort of constraint optimization problem where we, try to reduce the difference between the different boundaries, something feasible, but we know that it can be also complex regarding to the function that we choose as priors or the function that we fit. So what recommendations do you have for people who is trying to make use of this method where basically domains are decomposed, local analysis increments are computed? How can we merge everything in order to have consistency in the physics of the wall domain?
So I'm not absolutely certain I understand the question yet, but let me say what I think you're asking is that if your model has certain a priori constraints that you want to enforce in the posterior, is that basically what you're asking about?
Yeah, that does basically.
Yeah, so the underlying idea behind ensemble methods was that the prior is coming from this sample, and the hope is that that prior sample will do a good enough job in representing constraints that those will be enforced in the posterior. And so in many ensemble methods, including all the ones I made reference to today and the ones you made reference to, there is no explicit enforcement of constraints. And as an example, one of the ones that I constantly have users wanting is users want to conserve some quantity. As an example, a lot of climate modelers who get into data assimilation, they want to conserve the mass of say, the atmosphere, or they want to conserve the mass of tracers. And if you apply any of the methods I've been talking about here, that conservation would only, in general, that conservation would not happen. And so to enforce it, one has to apply additional a posteriori constraints, I think is the easiest way to do it. In many cases, I will argue with these folks, and this may not be the case in the example you have. So there's certain times where a model constraint is simply required in order to avoid numerical catastrophe with the model, and then you just have to find a way to do that. On the other hand, if you're talking to climate modelers and they're saying, well, we don't want the mass to change because when I run the model for 100 years, if the mass changes when I make model simulations, then the whole atmosphere leaks away or something else. But then you can say to them, well, do you know exactly what the mass of the atmosphere is right now? And if you don't know the mass of the atmosphere right now, then when you're using observations, you should be allowing that to adjust. And so I think it's necessary to have a discussion with users to determine just what they mean by a constraint like this and how important and relevant that constraint is. At the end of the day, you definitely have to come up with additional a posteriori methodologies, I think, to update this. Although I think some of our other speakers might have a different answer on this also.
Okay, excellent. So, Olga.
Well, thank you very much. I assume that we're ready to go right now to the next talk. I'd love to introduce Gary Benson. For all of you that already have been in the data assimilation field or the estimation field, we have been reading the book, reading the papers, and some of us were lucky to have a very close relationship with Gear. He this year offered us a very generous invitation to work on data assimilation to try to figure out what will be the best decision against the COVID-19 disease. Sadly, we couldn't join him because we are already busy working with machine learning, and that's another stuff. But today I invited him to tell us about how can we use the data assimilation techniques that he has been developing with all the team in Norway and all the group in Europe, and tell us how to use the data assimilation to understand the dynamics, and then finally try to help the decision makers to do a really good job. Welcome, Gear. It's a pleasure to having you here. And please share your screen and share with us your knowledge and your lessons and what we do to try to help with our mathematics and with our ideas. Thank you.
Okay, you can hear me?
Yes, perfect.
Yeah, and at least I can see my screen, so I know that's working now. Okay, so what happened was that back in March, this virus hit us quite heavily in Europe. We were all sent back to our homes or apartments, and we started working in home offices, and the situation was really uncertain for all of us. We didn't really know how this would develop. And also we saw there was a lot of misleading or strange information coming out through media from the government authorities, etc. And it was really, at least being a mathematician, it was really hard to accept explanations and predictions that came from the official authorities, because we saw that no one really understood what was meant by exponential growth and what the impact of having a too high R number would be. And then there was all these uncertainties of the severity of the virus, the consequences also for younger people with long-term effects, etc. So after a couple of weeks, I decided to start seeing if I could do something in using modeling and data simulation, and then to try to interact with the Norwegian authorities and maybe provide some advice based on my background in dynamical systems and etc. So the way this developed, I started implementing a model. I will discuss that more later. And we started running scenarios for Norway, and we used results from these simulations or communicated those to the Norwegian authorities, the health directorate, and there's an Institute of Public Health. And so we tried to support them with models. And in parallel, they also developed their own models. So in the end, there were quite a number of different model systems in use. At some point, I found the system to be quite robust and quite useful. And I invited a large number of colleagues in different countries to attend and also start using the system on their country's data. And in the end, we ended up with being, I think, 12 scientists in different countries running a system. And in the end, this also resulted in my largest publication ever in terms of number of pages. So the revised version of the paper is now 75 pages, and in the final journal format. And hopefully this will appear quite soon. So I'm working at NORSE as a chief scientist, and I have a secondary position at the Nansen Center. So this is to the organizers, just to explain the difference between NORSE and NERSC. And yeah, that was a joke. So this is the situation about a month ago on the global pandemic development. And as we see, the number of deaths is increasing linearly on a global basis. I considered updating the plots this month, but they look just the same. So there was no really any point. Just the numbers are getting higher. And we see that there is nothing that indicates that this pandemic is going to decrease or end anytime soon. And it's quite severe. The situation in Europe now is critical in most countries. We are seeing that in several European countries, they are now introducing quite strong measures again, or interventions to try to break the development of the virus. In other countries, you see nothing happening at all. So, or there are no interventions at all, and things are just going freely, like in Brazil and I would say some places in the US. So it looks like we are going towards a new complete lockdown in Europe quite soon. In Norway, it's not that bad. We have a few hundred new cases every day, but it seems we are able to control it. We kind of are on the limit of being able to control it. With a little increase in the number of cases, we would probably lose control and have to go to a full close down. But now we are able to isolate and trace all the contacts of all the cases, and people are being quarantined all the time when they have been in close contact with infected people. So what I will discuss in this talk is how we use ensemble data simulation for estimating parameters in a model for the the corona disease development. And I will compare it a bit with what we do in weather forecasting and also in parameter estimation studies. So this slide is a picture I stole from ECMWF, and it explains how they are using their ensemble data simulation system in weather prediction. So what they will do here is that they have some data simulation window, and here it's a 12-hour window in this case. And you have a prior, is a light blue ensemble. You make a prediction over the window, and then you compare with the black measurements. And what you see here is that you are not really matching the measurements very well. And then you are using the information from these observations to update the initial conditions for at the beginning of the window, so you get this green ensemble. So and then you make a new forecast over the window, and you are now closer to the measurements, and you continue the integration to make the new prediction, the ensemble forecast. And it's a bit different to what Jeff explained previously, because there it seemed to be a bit more sequential, but without a window. But in fact, you can formulate what he's showing in the same way. And there are some benefits of solving the problem over the window rather than just updating at the end of the window. But I might come back to that. And then if you look at how this compares to what we do in parameter estimation. So in parameter estimation, you have an ensemble of certain parameters of a model. So these are, I call these uncertain inputs. So in the reservoir modeling, for example, this is the characterization of the reservoir. So it's the porosity, probabilities, etc. And these inputs or parameters are going into the model or the model process, and you create an ensemble of predictions. And these are predicted measurements, okay? Then you compare with the measurements, and you use the ensemble statistics or the ensemble methods to update the initial parameters. And then you can run the ensemble again, and now you have an ensemble with lower uncertainties that fits better to the measurements. And this is a bit similar to what we had for the atmospheric as well, because in the atmosphere you had an ensemble of inputs at the beginning of the time window. Then you run your model forward in time, so you get predictions over this time interval or time window. You compare with measurements, and you update again the ensemble at the initial time of the window, and you make a new ensemble prediction that fits better to the data. And I wanted to show two slides just trying to explain what the ensemble methods are doing in practice. And here we see we have 5 prior parameter values going into the model. Then we make a prediction, and you get 5 prediction values. Well, these are then the predicted measurements, and we can compare these with the actual observed measurement, which has an uncertainty. So what we want to do now is to use the information from this measurement and with the information from the predicted measurements to update the inputs or the input parameters. In this case, it seems to be quite simple to solve this problem because there is an apparent trend in the model saying that if we increase the value of the input parameters, we're also increasing the value in the prediction. So maybe if you just move these particles up a bit, we will hit the measurements better. And that's exactly what you do. You are using what you call a statistical regression based on the ensemble correlations to update the input parameters so that you better fit the measurement. Okay, so in this 1D case, it's very simple to understand what's going on. If you have a multivariate system with, say, thousands of input parameters and also thousands of measurements, and then some of the parameters are going to be increase their value, others will decrease their value, some are not really influenced at all. And in addition, you can have a completely nonlinear system, meaning that you don't necessarily have this full monotonic behavior in the model. Then this problem becomes extremely mathematically complex. But that's what we are trying to resolve or do using these ensemble methods. So just to show the mathematics behind what I call this indirect data assimilation update. So we have the solution or the estimated solution at the beginning of the time window. And then we make a prediction forward in time to get the solution at xi plus 1, so that's the end of the time window. Then we have something called a measurement operator that relates this prediction to the measurements, and I call it h here. So that h of these predictions is the same as h of the model of the solution at the beginning of the time window. So this is just a nonlinear function. So you call it g of xi. And then you have measurements of y. And you want to combine this information and find the xi that gives the best solution. And this we can solve using a Bayesian formulation. So we have the prior distribution for the input parameters. We have a model integrating forward in time. So we get the predicted measurements, and we combine it with a likelihood function. And then you get the posterior density of the input parameters xi and also these updated predicted measurements given the data. And this is what we call a smoother update step in sequential data assimilation. If you look at the parameter estimation problem, it's exactly the same. You have a model of some inputs x, and this gives predicted measurements. We combine it with observed measurement, real observations here. And then we have exactly the same form of Bayes theorem or the Bayesian formulation. So that means the parameter estimation problem and the recursive data assimilation problem are solving exactly the same equations in this case. What we also normally do is to integrate out the y value from Bayes theorem. So, and that's done by saying that we have a perfect model. So the model is a delta function, and we put this into the integral, we integrate over y, and we get that x, the posterior of x given the data is the same as the posterior, is the same as the likelihood function times the prior PDF here. Okay, so this is the problem we are trying to solve mathematically. And just to illustrate what we are doing, we start with some kind of prior estimate of x. In this case, it's Gaussian. It doesn't have to be. We integrate the model forward in time, so we get a prediction PDF. And as you see here, this prediction PDF is non-Gaussian because the model is non-Gaussian. Okay, then we have measurements for the likelihood represented by the blue curve here. And we try to combine the likelihood with this PDF and update the input PDF. So we get a posterior PDF for the input variables, which is the black one for X here. And so this is the solution of this Bayesian problem. And then we just integrate ensemble forward in time to get the PDF of the prediction. So this is essentially what we will do now in parameter estimation, and which is also done in atmospheric weather forecasting using ensemble methods. Okay, so what we are trying to do is to sample this Bayesian formulation, or the posterior Bayes, and we do that by assuming that the errors in the data are Gaussian, and also that the prior for the parameters is Gaussian. And then it's possible to show that we can approximately sample for this posterior PDF by minimizing an ensemble of cost functions. So we have a cost function where you have the prior term here is a quadratic term, and then you have the data misfit term here. And this term will be nonlinear because the model is nonlinear. If G is just the identity, then this is a linear function, and then the solution of this problem is exactly the ensemble Kalman filter solution. If G is nonlinear, as it would be in using a nonlinear model in a parameter estimation problem, or if you have a nonlinear measurement functional and a nonlinear prediction model in metrology, then you have different degrees of nonlinearities introduced by this term, and you have to handle those nonlinearities. The simplest method to solve this problem is to just compute a gradient, set the gradient equal to 0, and find a solution. And that would be the standard ensemble smoother solution. And this was done already back in 1996. And in my book, there is a chapter describing how to use ensemble smoothers to solve this parameter estimation problem. Then there are two other popular methods that are used. One is an iterative ensemble smoother developed by Chan and Oliver in 2013, and an ensemble smoother with multiple data simulation developed by Emmerich and Reynolds in 2013. And I'm not going to go into great detail on these methods, but I think it's useful just to show a little bit why we benefit from using these iterative methods and what we are trying to improve using them. So, for example, if we use the ensemble smoother, then we take the gradient, we set it to 0, and we get this equation. And now we want to solve this equation for xj. So, to be able to do that, we need to do something with this nonlinear term. And normally we would apply a linearization or a Taylor expansion, saying that this g of x is g of the prior value of x times the tangent linear operator of the model times this difference. And since we now use a linearization, it means that this approximation is only valid for small updates, when the difference between the update and the prior is small. So that means if there are strong nonlinearities in the model in this G, then the ensemble smoother solution will be quite inaccurate in a way. Then another thing we do is to replace this tangent linear operator with a statistical regression term. So we compute what you call the model derivatives or the sensitivity matrix here with an ensemble-based sensitivity matrix, which is defined by the covariances between y and x and xx here. So that means we are using the same gradient for each realization. So that also introduces another quite small approximation. And then we use ensemble covariances instead of the exact covariances. So there is an ensemble approximation as well. And then there is a straightforward way of solving this problem. If you use iterative methods, then we are also computing the gradient, but we don't have to use a linear approximation for this term. So we reduce the impact of this linearization. And we are exactly solving or minimizing this cost function if we retain the Gj here, which is the tangent linear operator. But again, we would also approximate this one using the statistical regression. So in this case, we would also use a G defined by this covariance relation here. So we introduce a small approximation there. And then we could use these gradients and the Hessian in a standard minimization algorithm, a Gauss-Newton or whatever. And just to see what you get here, if you use the ensemble smoother, you get this full line and you miss the global minimum of the cost functions. If you use the iterative ensemble smoother, you get an iterative approach that converges to something which is very close to the global minimum. In the methods we used for this epidemic model is something called ESMDA, which is actually a recursive use of the ensemble smoother, but with inflated measurements in each step. And the way we inflate them is to say that we have the likelihood function here. We write it as the likelihood function to a power this sum, and this sum is equal to 1, so we don't change anything. And that means we can write it as a sequence of a multiplium of a number of likelihood functions. So what we will do is to use the ensemble smoother to solve this problem, where we have this inflation of the measurements. Then the result from this update becomes the prior for the next update. So we do a number of such steps. And again, that reduces, what happens here is that this reduces the impact of the linearization in the ensemble smoother. So we can, with a large number of such likelihood functions or such steps, we can reduce this to a negligible level. So this is a quite simple way of implementing an iterative type solver for this particular problem. And because it just means if you already have the smoother implemented, it's just a loop outside this and this additional inflation of the measurements. Okay, so if you go to the SER model, the measurements we had or have is mostly the number of hospitalized, and sometimes we have the different age groups and the gender as well. We have the number of deaths, both at hospitals and care homes, and then we have the number of positive tests. And then we know that at least early in the epidemic, the positive tests were highly underreported. They were highly biased because we only tested sick people or those with symptoms. And in fact, due to capacity issues, only those who had responsibilities within or worked in hospitals or were in contact with old people were tested. So these data are really uncertain. And also the different uncertainty and availability varied a lot in different countries. Also, the SER model, the SER stands for susceptible, exposed, infectious, and recovered. Doesn't predict the number of deaths and the hospitalizations. We needed to improve the model or extend the model to cover these variables as well. So what we developed in the end was a model that looks more or less like this. So you have the susceptible, the exposed, and the infectious. And then we also split these into different age classes because, well, first of all, we know that the old people are more likely to die or have severe disease than the young people. So they would have different coefficients in the model. And also we wanted to model the development within different age groups. So what happens is that you have your susceptible population and the infectious, people are interacting with these ones and they get exposed to the virus and end up in this exposed group. And this develops to become infectious. And then at some point, after you realize you are sick, you end up in a quarantine group where you basically stay home and isolate yourself. And then we have three groups here: those with mild symptoms, those with severe symptoms, and those with fatal symptoms. So those with mild symptoms just recover. Those with severe symptoms go to the hospital and then they recover. And then those with fatal symptoms are either in a hospital and where they die, or they are in care homes or maybe at home and then they die. So what we measure is the total number of people in the hospitals, the total number of deaths, and in some cases the total number of cases. And the cases would typically include the infectious and everything to the right of the exposed. Okay, so the equations for this system are quite simple. It's just a flow of people through the system from susceptible towards either dead or recovered. And there are time scales defining how fast they flow. And this R number is defining the infection rate of the susceptible population. So if R is less than 1, then we know that the disease is going to die out and disappear over time. If it's larger than 1, then we get an exponential growth of the number of infections. Okay, so there are quite a number of parameters in here. We have all these time scales, and there are some estimates of these time scales, but we also try to include them as parameters in the data simulation. In addition to that, we have these p fractions that say something about the number of mild disease, the fraction of severe disease, the fraction of fatal disease in the different age groups. Okay, and also, of course, the sum of the right-hand sides is equal to 0, so that the total change of people is equal to 0. So the validity of this model, we can discuss that. We are using aggregated variables. So that means you need a certain number of people in all of the groups to have statistical significance. So this model is different from more individ-based models or particle models, where you model each person as a particle and then you use some kind of statistics to compute the likelihood for interaction between different people, and you model how people are moving between cities and countries, etc. So it's quite a simplistic model, but still it has been proven to give quite good results in large epidemics. And also for our case, it gave us the possibility to model the epidemic very quickly and get results very quickly. Yeah, and so the model neglects the import of cases, which I think was okay during the lockdown because no one was traveling and no one were really moving around anywhere. And then we had all these different parameters that we set. These were set as constant, and they were based on international data or estimates at the time. And what you see here is just that the fraction of, say, fatal disease is much larger in the old age group between 1905 than it is for the children. So it's just a way of modeling how the disease is evolving among different age groups. So this we didn't try to estimate. These are the parameters we estimate. This is all the time scales. It's these overall fraction of the case fatality rate and hospitalization rate, and the initial conditions, the number of initial infectious, the number of initially exposed, and then most importantly, the effective reproductive number as a function of time. And of course, this number is dependent on how we as people behave. It's dependent on the interventions that are implemented or imposed by your government. So it will have vastly different values in different countries. We spent a bit of time on trying to model the effective reproductive number. So we said that R is a matrix, and that means it can have different values within and among different age groups. So, for example, we can increase the number of infection among the elderly, which happened early in the epidemic when the infections hit the elderly homes. We can increase the number of infection among children when they started going back to school, and we have an example of that. And we could also increase or separate into different ethnic groups and or demographic groups, different demographies, and model how different populations interact together. So these interactions are given as a constant matrix, and then we have a time evolution of the overall effective rate, which is steered by how people isolate or interact. And what we see is that the behavior in the population 2 weeks ago determines today's deaths and hospitalizations, because it takes some time from when people are becoming sick, until they end up in hospital or die. So we cannot estimate today's R value. Okay. And then we can make assumption about R for the future. So we can maybe learn how different interventions impact R, and given our planned interventions, we can say something about what R will be in the future, and then we can run scenarios based on that. For data assimilation, we used ESMDI since it's very simple to implement and use. It's also very efficient for large ensemble sizes, and that was an important point. And in this case, we used 5,000 realizations and 32 ESMDA steps. And this is a complete overkill in the number of realizations and ESMDA steps compared to normal data simulation applications. But we did it because we could afford it, and the model is running so quickly. So we could basically eliminate sampling errors, and we could also make sure that the ESMDA method is completely converged. Okay, so this is just one example. It's one of the first examples from Norway. And in this case, we used measurements up till about 1 week into July. And we see how the model is able to predict the evolution of the number of deaths with uncertainty, and also the number of hospitalized. And this exercise became less interesting at the end of July, because we had almost no cases left. There were this is the number of cases, 50 here, right? So we had like 20 cases or 20 people in hospitals at this point. And there were almost no one dying. So in Norway, we thought everything was completely under control. This is the estimate of the R value. And what we did here was to use a prior with a high value for R initially, like 4.5. And this seemed to be quite a correct estimate, or at least to be able to cover the growth of the disease at an early stage. And then we estimated R, and after the interventions, which started about here, we had a rapid decline of the R, and it went to as low as 0.2, 0.3. And basically at this time, at the end of March, people were not going outside. Everyone was staying inside. No one were allowed to travel anywhere. And people were basically hiding, and because no one knew how dangerous this would be or not. And essentially, we killed the whole epidemic in 2 to 3 weeks. And then we saw that the R number started to increase again, and it stabilized around 0.8. And then what we did in this case was to run a prediction till the end of mid-October or so, and using this stabilized R value, and then you see that everything looks really nicely. However, what happened was that in July, people were allowed to start going on vacation again, and they were allowed to travel to countries with also low number of infections, and among those Spain and France, Italy, etc. But the point is, when Norwegian travel, they don't mingle with the Spanish. They go to the bars and they mingle with all the others that are on vacation, and go partying and having lots of fun. And then that's, of course, where you get infected. So people started coming back to Norway with infections end of July. And then in August, they all started school again. And we had all the new students starting universities with tons of parties and celebrations, etc. And we got a second bloom instantly based on this. And right now we are still fighting the effect of this second bloom, and we typically have 200 to 300 new cases in Norway every day. In Bergen, where I live, we had up to about 50, 60 cases a day, but today I actually saw we were down to 8 new cases. So it seems like now we are going to stabilize it again. Another problem we have in Norway is that we import a lot of workers from Poland and other European countries, and a large number of them turn out to be carrying the virus, and so we import new infections. And we are not really rigid in the way we test and isolate the people that are entering Norway. So, but anyway, we are trying to manage the disease. We're trying to avoid these extreme exponential growth of cases, and it's done by testing everyone that feels sick, and then trace all where they got infected, and quarantine everyone they have been in contact with. So for now it seems to work, but it's still it's an unstable situation, and if you mess up a little bit, it just goes really bad again. Yeah, and also this is a log plot of the same thing as I had above, but here I showed the number of active cases, and you can see that by September there would be less than just a few hundred cases left in if we had continued the interventions and the behavior. So, and this is an example from a bit earlier in the pandemic. It was run after the first week or second week of April, because at that point we were discussing if we should reopen schools. And what we wanted to do here is to make predictions or scenarios of what would happen if we got increased infection spreading among the children. And so we ran 3 different scenarios based on this calibrated model. One was the steady state scenario, where we continue with this 0.8 R value, but with an uncertainty. So then things looks quite okay. The disease is continuing to die out, and it would be what we hoped for. Then this is a more unstable scenario. It's a neutral scenario, but where the R value is around 1, and then you see that you are not reducing the number of hospitalizations; they stay more or less constant. But and the same with you have a linear increase in the number of deaths. And then we had an unstable scenario where things really go bad. But these are just small changes in the R value, and you see that you get really vastly different behaviors of the system. And so this we communicated to the Norwegian government, and but then what turned out was that if you looked at the previous case, was that even if you open schools, it seemed like R stayed quite low. So in our case here, we were quite pessimistic in these cases here. So it turned out that opening of schools, of course, increased the exposure among the children, but at the same time, the rest of society was able to keep the R value down by still working from home offices, etc., and avoiding public transport. The bars were still closed, etc. Okay, so then we ran a lot of sensitivity studies. We ran for the Netherlands using different priors for the R. Here is the same as we used for Norway, with a constant before and after interventions. This is one where you had a large prior, constant prior for the whole time period, and then you estimate the R, and then you see that they are not so different. You get more or less the same behavior in the R value in all these cases. This is another one where they use the publicly official R value from Holland as a prior with an uncertainty, and again you estimate the one from your model. And yeah, so probably this is too low here, and then the actual R value of the interventions were quite a bit lower than the assumed one from the government. But now, you also see there was a lot of uncertainty in the prior here, so you get unstable solutions also in the predictions. In Argentina, we also made some longer-term predictions, and it's quite nice to see that in this model we only used the death data because they didn't have enough hospitalization data. But then we ran different scenarios with different prior R values. There's one stable, there is one unstable, and one strongly unstable, I would say. And these are the three different resulting scenarios. And at the end of August, they had about 8,600 deaths, and that's about here. So it seems like the expected scenario, this central scenario here, is was the most likely one, and it seems to be quite correct. So that means you have made a prediction from end of May till end of August, which is quite accurate. And that kind of shows how you can use the predictability in a model if you have some knowledge about what are. So this is the way we will try to use it in the future also. In the US, I'll show you the next one. This is very interesting because we got results with a lot of oscillations in them. And you see we have oscillations in the data as well. And then we see that we have similar oscillations in the data, in the estimated R value. And these increases and decreases in R value corresponds to generating or reducing infections that we observe in the hospitalized or the deaths 2 weeks later. So that means we can actually track time variability of the number of infections using the model and the data. And this thing of having a time-dependent R value is quite important. And I think we are the only one who has done that so far. So in the US, they were able to track the epidemics for the whole time period we had data. And we could also connect some of these maxima and minima to events in like big manifestations, etc. in the different states. In the UK, I just wanted to point you to this web page. There is an ongoing, they are running the system operationally and producing updated models and predictions on at least, I think it's a weekly basis. So you can look at that later on. And then I have a summary slide, just to summarize what I've said more or less. So the data assimilation system is able to track the epidemic quite accurately, and we can estimate the past R of t value. It's possible to quantify the impact of interventions. We can do short-term forecasting using R persistence. That seems to work quite well, say for 1-2 weeks into the future. And we can do long-term scenario forecasting where we have to say something about the future R value, depending on what the politicians are deciding. The code used for all these examples is available from my GitHub page. Apologies to Olga's group for using a really early version of it and some initial struggles, but now it's supposed to be quite a robust system, and all the different countries or the scientists using it were able to compile and run it, setting up very quickly. So there is actually used by a large number of students now. So that was the advertisement. Then there's a manuscript on GitHub. This is the version 1 of the manuscript. There's an extended revised version that's I haven't made it publicly available yet, but I hope it will appear quite soon. So you can, if you write me, I can send you a copy of that. Okay, so I think I will stop there, and I will make the presentation available, send it to you by email, and I can take some questions.
Well, thank you very much, dear. This is a very interesting application of data assimilation. I assume that we already have a lot of questions right now, so I would love to open the microphone to Arnold, to Elias, to Jeff, and also invite the students and the people watching us through YouTube to ask questions that you need to have answered. And also, I send my warmest regards to the practitioners that are trying to learn how to use the data assimilation in their own applications. Well, Arnold?
Yeah, you hear me?
Perfect.
Is it possible to ask a question like that? Yeah, okay. Thanks, Geir, for the very relevant application of Ensemble Camel filter. I have a question about the parameters. As you already mentioned in your presentation, the more complex the model, the more parameters you get. And if you introduce age distributions, you have to know something about their interaction between the different age groups. Do you have this parameter, or do you include this in your ensemble methodology, or?
No, we specified that interaction. We thought it would be we didn't have enough data to estimate those values.
Yeah.
If we had more accurate data of the number of infections per age group, I think we would be able to improve on that. But for this particular application, we did not. So in the UK, we had some scientific papers discussing this R matrix for the different age groups. And so there they actually had some scientific basis in the way they specified. In the Norwegian case, we used it to just by increasing the infections in the 2 age groups that are going back to school, and also somewhat towards their parents. And then you could, if you start model the results for the different age groups, you would see that you get higher number of cases among the young ones, but it doesn't increase the number of deaths or the hospitalizations because they all have mild symptoms. That will come later.
Yeah. Okay, and maybe another question is about the model for the parameters. Are they constant or slowly varying? If I think of the Dutch situations, the rules changed continuously, and also the people at some point didn't follow the rules anymore. So you may expect that the parameters are not really constant, but they are kind of slowly varying.
There are different things that are specific for this study, because this was done over a 3-month period early in the pandemic. And I think the parameters themselves were quite constant during this time, except for the R of T, which changed quite a lot. And that's, of course, when people change their behavior, you also impact R. But as soon as people start going to pubs and bars again, you get an increased R. So then you get increased exposure. Yeah. What we see now is that we know more about how to treat patients. So the death rates might go down a bit. So that means the case fatality rate has changed with time. And here it was used as a constant. Other things is that we see that also that the spreading of the virus is different in society now. It's more mainly among students, and at least for the last month or so. So it's a younger generation that has a lot of cases, and we are able to protect the elderly better in their care homes, so they are not exposed to the same level. So that means also that the death rate will go down because of that. So that means if we were running again the whole system, I would use a time continuous case fatality rate and hospitalization rate as well. And I have a version of the model that's doing exactly that. Also, the model, we extended the model to run with multiple populations. So we can model, for example, all the states in the US. We can model all the countries in Europe, and with data sets for each country. And then we can have interactions between the countries that you specify according to how people are allowed to travel between the countries. So then that means you will account for the imports of cases, etc. And this version of the model is now used in the US. There is a group of students from a summer school this summer who started working together on this system, and yeah, so it's quite exciting what they are doing.
Okay, thank you.
Yeah.
Thank you, dear. Elias, do you have any question, Jeff?
I think this is, first of all, thank you very much, Gear, also for your talk. It was very nice. Well, my question is more related to the, as Arnold mentioned, the parameters, I mean, the distribution of the parameters. So it seems like you have plainly identified that some of them are changing in time. Are you planning to do anything with that? I mean, are you planning like to fit maybe, I don't know, maybe a non-Gaussian model for those parameters, or to make some assumptions in that direction?
But first of all, I think these parameters, we probably don't see it now, but the timescale parameters are probably quite constant in time, and they are not so critical for the model. What I would need to do is to include time variability on the PF and the PS. That's the case fatality rate and hospitalization rate, in addition to the R numbers, and that I have in the latest version of the model.
Okay, that was basically my question.
Yeah.
Well, we have 26 people watching now on YouTube. I have a question / comment. You already know that I'm a former control engineer, and the kind of estimation of parameters or states are being developing through years is more oriented to closing the loop of control. And I can tell that the model estimates very well the parameters, but I really would love to have some of the prospective view and the control actions view. In order to use a model to make decisions, we should try to design a model-based predictive control. Have you ever think about to include the control actions into the model in order to close the loop and trying to use the estimation to figure out the progress? I can tell from my own developments on the small models that I can close the loop with a Bayesian estimator with a deterministic controller. Are you working on that right now?
I've not been working on it, and I'm not a control engineer. I had some discussions with control engineers about this early on in Norway, based on different scientific groups trying to contribute to this topic. What they proposed to do was, which I killed completely, was to use the feedback or control to decide what kind of interventions they would need to keep the infection level at a certain controllable level or acceptable level. Because when you work with control theory, there's a difference of working with stable systems and completely unstable systems like this one. Because if you have a completely unstable system, then you cannot really control anything. You will have to update the controls all the time to be able to control the solution, right? And what I could show is that the best way to control this system is to just kill the infections. And when there are no more infections, then you don't need to do anything. So if you reduce the number of infections to, say, 100 in Norway, then we say that, okay, this is an acceptable level. So now we start releasing the controls or interventions. Then immediately the number of infections will start increasing again. So you have to start shutting down again. So it's a really difficult way or it's not a very economic way of controlling the system. The best is to get rid of the virus and then live as normal. So that was my opinion. Because if you're at this level, it doesn't cost much to completely eliminate the virus. But then of course there are so many different issues that are considered by the politicians, like the economy of the country, the importance that people can travel, all these things. But then I think there are a couple of countries that have done things right. And one is New Zealand, the other one is Australia, which basically close the borders and say that if you go to those countries, you have to be quarantined for 2 weeks. And in fact, Australia doesn't allow anyone to enter Australia unless you have a permanent residency there. And when you arrive, you are tested, you go straight to a hotel, and you have to stay in this hotel for 2 weeks until you are let out in society. And the big second bloom they had in Australia was caused by people escaping the quarantine illegally. So it's saying something about how complex this situation is. And I'm a bit annoyed by the Norwegian government who do not impose strict quarantines on everyone arriving to Norway. They are supposed to quarantine, but no one controls it. They can basically do what they want. So it's a trust-based system. But of course, generally, I would say that almost every nation in the globe has managed this wrongly. And that's why we are where we are today.
Well, thank you. And in terms of our uncertainty quantification, we can also, I assume that we can also use your model in order to try to set some boundaries for the kind of uncertainty that people introduces into the model. Have you ever think about using the PDFs or the main findings in order to classify the kind of countries or cultures through data assimilation results?
My student friends in the US are doing that. They worked with different ethnic groups in the US that are hit differently by the epidemics. And of course, we see that in all the southern countries, the Latin countries, people are kissing all the time, and you are much more exposed to the virus. In Norway, when we were told to keep 2 meters distance, we kind of said, yeah, well, that means we have to get even closer than normal. So it's there are different cultures and we behave very differently, and that has a big impact on the spreading of the virus.
Well, thank you. It's very nice to see how we long time ago started with small scale models, and then we moved towards large scale models, which is numerical web prediction or reservoir management, and then we are back to small models, and we're still having the same troubles we had at the very beginning. Thank you, dear. I'm very pleased to have you here. I'm sure that our students, our research students, are going to take advantage of your work. And I for sure hope to have time to tackle the problem here in Colombia, which is a very complex stuff. Thank you very much. I will move towards the next talk. Elias, please. I'm very, very happy to share with you the most recent work of Elias Niño, which is my partner in data assimilation here in Colombia, has been helping me a lot since the very beginning we met. Elias, thanks for sharing with us your talk, Efficient Ensemble-Based Methods for Sequential Data Assimilation. You have 4 minutes, and thanks for joining us.
Okay, yeah, just give me a second. and I was pretty sure that the next one was Arnold.
Oh, I am so sorry. That's my bad. Sorry.
Yeah, but so let Arnold go. It's okay.
Yeah, Arnold, are you there? I'm so sorry. I apologize.
Yeah.
Yeah, you're there.
Arnold.
Yeah, Arnold, so you're there. That's good. This is work.
Okay, we were both
Okay,
really
Arnold.
very surprised. You were suddenly, yeah.
Welcome back. Arnold.
It was a surprise. It was a surprise for me as well. So. Okay, Arnold.
Everybody knows that I'm kind of crazy, but yeah. So I will introduce Arnold Hemming. Since oh my God, a long time ago, 5 years from now, we met in the Netherlands the first time I went to Europe, and he was very open to receive a Colombian professor and Colombian students, and we have been working together for 4 years now. We have a joint project, which is what was called data assimilation for Colombian geomechanics, I assume that. So the first part of the story is that Arnold was working with volcanoes, and he asked me about working with chemical transport model for volcanoes, and he told me, I know there's a lot of volcanoes down there in Colombia, but I wasn't pretty sure about willing to work with volcanoes. It happened that we were concerned about our pollution, and we decided to use the Lotus Zeros model in order to develop new techniques of data assimilation. So we moved towards the research on the ensemble-based data assimilation for chemical transport model, and in parallel, the twin experiment with the variational data assimilation. What happens is that the chemical transport models are very complex, and it's not necessarily easy to develop a variational approach. I apologize, Arnold, for completely forget about the talk because I was just looking at the two computers. And Nicolas is also asking me why you let Arnold go. So my apologies in front of everyone. And I will be very happy to hear from you, your talk, a joint free for DVAR. Speaking of which, we are going to have tomorrow a session on 3D VAR and 4D VAR applications. And I am pretty sure the students and all the people will be prepared for tomorrow's sessions. Thank you, Arnold. The knight in the order of the Dutch Lion.
Okay, thank you, Lucia. Can I share my sheet? I never use this system, so it's always
very easy. Share screen and then give the computer the entire desk.
And then I can select something.
So meanwhile, Nicolas is bullying me for my mistake. Warmest regards to the TMO Sport 2 research group. And if you have questions, please feel free to ask it. Okay, there we go.
Do you see some?
Yes, we are ready to go.
One moment.
View full screen, and I think.
Yeah, but that's right. Let me see where is full screen. Okay, but I can't see myself anymore. Is that correct, or is
It's correct.
Okay.
We can see your screen. Go ahead.
Okay. Thanks, Lucia, for inviting me again. Of course, I would have loved to come to Colombia again and to have the workshop in Medellin and have a holiday afterwards, but Corona viruses made this impossible, but I'm happy that we can do it in this way. I'm talking about a different topic, adjoint, free 40 VAR. I work at the University of Technology, and we are involved in many different type of application of data assimilation. And usually the modeling part has already been done. So my colleagues from other faculties, they have numerical models for reactor physics, for atmospheric chemistry, for the Maxwell equations, for even in finance. So we are involved in these projects for doing data assimilation experiments, and then building an adjoint for such a model is completely out of the question. I will never ask my students to do a programming effort for a few years for building an adjoint to be able to solve 4D-FAR problems. So most of the problems we handle ensemble type methods, like the ensemble Kammer filter. That's usually the way to proceed. But for some problem, we would prefer a 4D-FAR approach, a variational data assimilation approach. And but then we were confronted with the adjoint, and we try to develop a methodology where we can escape from coding the adjoint and have a solution which is as close as possible to the 4D-FAR approach. We have built this in the recent years, and what I'm going to tell is based on the two papers I have written here. The first paper just appeared, I think, 2 weeks ago in Journal of Computational Physics. It's kind of the last piece of the puzzle of the whole methodology. It consists of different components which we merge together to make it a tool that can be, it's model independent, just like a ensemble Kammer filter, and it combines different standard tools from numerical algebra, and I will explain a little bit more. And the second paper is that we applied the methodology to a complicated 3D reservoir model, and we compare it with the a kind of black box approach, a deep neural network. I'm not an expert in deep neural networks. That has been done by one of my colleagues, but I have some results that I use to compare our own methodology. Okay, and the acknowledgement, Chong Chao, that's the student that did most of the work and the experiments. He is finishing now his PhD degree. He submitted his draft thesis last week. Olwijn Leeuwenburg, he is our expert in reservoir engineering. Hai Changling is more interested in the computer science aspects, deep neural network and high performance computing, and I'm the other one. Okay, so what is the idea? I will first tell you a little bit about the motivation. Why are we doing this work? Why did we start it at all? Then the different pieces of the puzzle of the whole methodology, which consists of 3 components. First one is model order reduction, where you try to find the subspace where the action is, and that you need to include in a simplified model. Then the trick, the first model order reduction, proper orthogonal decomposition, it's standard. It's not new. It's already there for many years. A very powerful method. The complication occur when you extend the methodology to a nonlinear system, and then you are confronted with you need knowledge of the underlying differential equations. It becomes intrusive in the sense that you have to do a lot of programming to get things done for a nonlinear system. And that's the thing we would like to avoid, of course. And the whole methodology is to not have to change or develop the code or to be aware of the underlying physics in the system on the code level. So the key point is that we had to develop is a non-intrusive way for nonlinear system. Non-intrusive in the sense that we can still use the model as a kind of black box. And then to scale it, that's the last component that we kind of solved recently, and that is in the paper that I showed you before, and that's domain decomposition, and that makes it possible to apply it to parameter estimation problem with hundreds or up to 1,000 parameters with a limited computational effort. It's still a tough problem, of course, but I will tell you more about it later. And then the comparison with a deep neural network, which is more black box. And I will illustrate the methodology, in this case with two applications, one with reconstructing the bottom topography in a coastal sea model, and the other one is permeability patterns estimation in a reservoir model. Okay, first motivation. So I already explained that we usually use a ensemble comma filter, both for estimating state and also for combined state and parameter estimation. And that for many applications, it works perfectly. No reason to jump to another method. But for some applications, we had problems. And then the ensemble comma filter showed filter divergence in the sense that the results of the filter are statistically inconsistent with the actual estimation errors. It's a quite common approach, which well, there are tricks to handle it, of course, but first, why does it occur? I'm interested for our adjoint free 44. I'm interested in applications where the model is complex, where the number of parameters are very large, and especially when we have a lot of data. We talk about hundreds, thousands of data points that we would like to include in the estimation algorithm. And if you do it in a recursive way, using a reduced rank approximation of the covariance matrix, then you will lose information. The idea of the comma filter is that it is a sufficient statistics, that in the sense that the mean and covariance matrix represented by the ensembles, they contain all the information from the data in the past, and if that's a lot, then it's very hard to keep this information in the covariance representation using a reduced rank algorithm or representation of the covariance matrix. So you lose information. And if you have a lot of information and long time series, then at some point the results are not accurate anymore. And of course we can include localization that helps a lot, but then you change the problem a little bit. So what makes things worse, if we have a noisy dynamical system, then there is not really a problem, because all data is not very useful. The filter is exponentially stable, and old information is automatically forgotten, and then the problem will not occur. But if you do parameter estimation, and that's the problem that we would like to handle or solve, then the parameters are constant, and then all information from the past is useful and should be included in the algorithm. Okay, and that what we usually do, if it's not working, then we add a little more noise, and then the parameter become time varying, and then after the whole simulation, we average the results again. So that's a kind of engineering solution in order to get good results with an ensemble Campbell filter. But so the idea is what? Here is typically an application where we got the idea of let's do it differently than using an ensemble estimation procedure. Estimating the bottom topography in a coastal sea model. The idea is the problem is pretty big. It's a numerical model with a kind of 1 million grid points, a time step of 2 minutes in the numerical system, and we have calibration periods, preferably over a year. So it's really one simulation is a lot of work. And we have a lot of data. We have hourly measurements over a year, and then in 50 tide gauges. So we talk about 150,000 data points. So it's a huge estimation problem, and if we tried a ensemble Campbell filter, and indeed how we did it was making the algorithm slowly varying and then averaging at the end, and then we get reasonable accurate results. But we think, okay, this could be better maybe if we start from an alternative, and which is 40 var. Well, just I don't summarize 40 var and the derivation, but just the main idea of the algorithm is that you start with an objective function. The idea is we move to solving the data assimilation problem as an optimization problem, and then minimize the criterion. So we have a criterion depending on the parameters. We have the first term is the misfit with respect to the data, and the second term is some kind of prior information in the parameter that's not relevant. And the algorithm is you run the forwards model, where is the X is the state of the system. You have a nonlinear model, so you run the model forwards in time, and then the second equation of the system is you run the adjoint system backwards in time, where the adjoint is the transpose of the linearized forward system. And then once you do this, you have the gradient of the criterion, and then you get a next step in the estimate of the parameter. Okay, this is great, but you have to develop this F operator, this tangent linear model, and then transpose it to get the adjoint, which is a system that runs backwards in time. Then, and that's a lot of work. So no way that we are going to do this for very complicated modeling system, which consists of many sub models which are interact with each other, that have been developed over 20 years with input from many different PhD students. Sometimes colleagues don't even know exactly what's going on, but the system gives nice results. So that's not a way to proceed. Okay, why would this be attractive? Well, I think for many applications, ensemble filter do a great job, but if we have deterministic estimation problems and also problem with a lot of data, that's crucial here. Then adjoint-based methods are in principle attractive. And yeah, this is what I already said. The building the adjoint is too much work, and another disadvantage is that the problem is non-convex, so you have local minima, and that can hamper the applicability. Although this is not really a problem that we have occurred, have observed a lot of time. Okay, now what is the idea? We don't want to develop an adjoint, so what can we do? We can first derive a approximate model, approximate non-linear model, and then use this model in the whole loop of the optimization scheme. So instead of going for the original model, we try to approximate the forward model as accurate as possible. And of course, it should be a model that is easy to solve, or where the adjoint is easily available, because we want to escape from developing complicated adjoints. Now, basically, surrogate models, we have two options. One is a bit physically based, mathematically based model order reduction, where you step by step know what you're doing, you know the error that you make. So it's really, you have things under control, and you can make the algorithm tailor-made for your application. And then, of course, it's more straightforward, black box. It's a deep neural network where you try to generate information about the underlying simulation model to derive a new model, and then use this model as the whole in the whole algorithm. And the reason why it's possible to get accurate results in this case is that it is part of an optimization algorithm. So you don't need an approximate model that can reproduce all the information of the original model. That's way more complicated. What we have to, what we need is a model that is only able to reproduce the relation between the parameters and the data. So if the reduced model or the surrogate model is not able to accurately reproduce results in a remote part of the domain where there are no data points or where there are hardly any parameters, then that's no problem that the model is not accurately at that point. So because it's part of the optimization, it is only important that the surrogate model is able to map the parameters accurately to the data and vice versa. Okay, now what is the basic idea? What model order reduction is way more, it's more gray box, or it is not black box, because we know what we're doing. And the idea is the first piece of the puzzle is to find a subspace where the model variability is large, and that is of course the part that should be included in the reduced model. And once we know the subspace, we can project the original model onto this subspace. And as I already explained, that the major challenge is here to develop an efficient methodology which is non-intrusive, in the sense that it is not requiring access to the code of the original model. That's not common, and there are many ways to develop a reduced model for nonlinear system, but they are intrusive. They require knowledge of the system, the equations to handle the nonlinear terms in the underlying model. Once you have the reduced model in this way, then it's easy to use it in an optimization scheme, and then you use this formulation to estimate the parameters. Deep neural network is similar, but then you train the neural network to reproduce the model so that this network is able to be used in the optimization scheme. That's quite a standard tool, and in both cases, the optimization, once you have a reduced model, the optimization is completely, it's very cheap. So it's done in reduced space. So the key problem is to get the model, and that's where the computations computational effort is used for. A major difference of model order reduction and the deep neural network is the training. In the model order reduction, the training is neglectable. If you have the ensemble of model simulations, that's the only part of the algorithm that requires a lot of computations. Then getting the reduced model is simply standard tools from numerical linear algebra, eigenvalue decomposition of relatively small matrices. Deep neural network training of the network is the dominant part of the algorithm. So the training there is huge, and we need high performance computing to get the model. So that's a major difference, and that is also hampering the application to very large applications of a standard deep neural network. So what is done is usually you make a reduced model, and then you use this methodology to estimate the parameters in reduced space, and then in principle you go back to the original model again, and you redo the algorithm. So you are at another part of the subspace where the action is. You are at a different parameter, and then you can do the same again, and you explore the cost function close to this parameter again, generate new ensembles, make a new reduced model, and repeat the experiment. So that's what's done in the reduced order methodology, the first one. In the deep neural network is hardly possible, because that's making a new reduced order model is very time consuming. Okay, let's, I think time is running short. Maybe I think I skip some slides with respect to the mathematics. So I focus on a more general idea. And so the first step is model order reduction, and that's the standard way of doing this is, or the most famous way to do it is proper orthogonal decomposition, and that's very well founded. It gives the subspace where the model variability is dominant and it's large. And once we know it, we can reduce the original model and project the original model onto this subspace. Okay, then I forget the equations. Because of time, I want to show some results. So that step one, we know the subspace where the action is. That's and then the next step is make the methodology able to do it for nonlinear system in a non-intrusive way. And that's also, it can be done in very different ways. Yeah, if you do it in a intrusive way, it will not cost any additional computational effort. If you know the equations, you can use them just like with the adjoint, but we want to do it with additional model simulations to get the nonlinear part of the reduced model to have the additional terms that we need to represent the nonlinearities in the model. So again, the mathematics I will leave, and I will focus. So this is one way, and I will focus on the final flowchart of this methodology. So what you do is you have a set of parameters you want to estimate. You run the model, high order model simulation. You evaluate the objective function, so that it's all done with one model simulation. And then if you have not converged, which is generally the case if you start, then you build the reduced order model. That's the red part. That's the time-consuming part, and that's really where all the computational effort is needed for. And then the blue part is completely peanuts. It's you can iterate it, you can solve it in different ways, but that's very cheap. And then you get, of course, new parameters, but since we did everything in reduced space, it doesn't need to be the final answer. So you go back to the high order full model simulation. And then if you are not happy, you start again with building a new low order model. That's the idea. And of course, we want this red part to be, that's the time consuming part, and we don't want to visit this part of the algorithm very often. Okay, so some remarks of the algorithm. The computational effort is usually dominated by generating the reduced order model, and that is that the number of model simulation that you need for this is roughly the dimension of this reduced subspace plus the number of uncertain parameters. So that's quite a lot. So if we, well, I show you some examples later on. If you do more outer loop iterations, then it only requires one additional model simulation. So that's not a lot. So really the step one is the most dominating one. You have to do a lot of model simulation to get your first reduced model. To update it is more easy. And the number of outer loop iterations are also usually very, very small. So it all boils down to the first remark. The number of model simulations is kind of proportional to the number of uncertain parameters, which is, well, can be still a lot. But the most attractive feature of the algorithm, and that's what we have in the case that I showed you, is that if the reduced model is time variant or even periodic, then we can generate the reduced model with very short simulations, and then we have a reduced model, and we can use it for calibration periods that are way longer. And that's typically the case we have in this tidal model. So here is we apply the whole methodology to the tidal model, and then same picture, but now we have a very computationally heavy application, but for deriving the reduced model, we need only simulation of 3 to 4 days. We have some startup phase, and then these short periods contain all the information from the dynamics of the system. And then we have a reduced model that can be used for the whole simulation period, which is typically 1 month or even a year. So that's the kind of the perfect conditions that we have. So the physics can be, the information that we need can be gathered only with a whole bunch of short simulations, and then the physics is already included in this simulation, and then we can build a reduced model, and then we calibrate over a long period. And that's of course very special case. This is not general. So we did it. We apply it, and both for periods of a month and a year, and it works fine. What more important is the computational cost. So the first step was 20 parameters period and a calibration period of 1 month. And then for estimating 20 parameters, you need 11 simulations to get the final answer, which is not a lot. If we do the same parameters and we estimate the parameters over a year, then the number of simulations that you need is only 5. So we need more simulation, but only these short ones. They are at some point neglectable compared to the simulation you need for the outer loop that we have, which is in principle only 1. So you need way less model simulations than the number of parameters. So this can be scaled up to easily to much more parameters, which is also done now. Okay, but that's the easy part. The complicated part came when we were confronted with permeability patterns estimation. So that means that the reduced model now is time varying. There's no way that we can do it as a constant or system. So that means that the reduced model is different at any time step of the original model. So you have to store a whole bunch of small models to be able to reproduce the full system. So then the computational effort is more. So here I skipped the underlying physics. So here, this is what we want. We have the permeability. We do twin experiments. So we know the reality, kind of. And then here, this is not a very large-scale application. We still have the straightforward finite difference approximation of the gradient. So this is the finite difference solution is more like what the adjoint would produce, the full adjoint. And the reduced order model is really reproducing it rather well. If we look at the cost function, you typically see that the black line is the finite difference, which is of course very time consuming, but it's the kind of ultimate method that we would like to approach as accurate as possible. And you see that the reduced order model is less accurate, but after 50 iterations, the next outer loop iteration starts, and then the final answer is in terms of the cost function the same as the finite difference approach. Okay. So here it was we estimate 44 parameters and it took 112 simulation. That's quite a lot. So still we are not happy in the sense we want to estimate more parameters and we want to have less model simulations to be able to really use it for large-scale systems. And then the final answer is the third one is domain decomposition, because that makes it possible to split up the domain in a whole bunch of small ones, and then the computational effort is really dominating by the computational effort that you need for your small domain. So this is the basic idea. We knew that the number of model simulations to derive the reduced order model is proportional to the number of a certain parameter and the dimension of the reduced model. Well, for large-scale model, that makes it not attractive. So if we introduce domain decomposition, then the computational effort is approximately the dimension of the reduced model and the dimension only in one of the subdomains, plus the number of uncertain parameter in one domain. So that means that the speed up is a factor of equal to the number of subdomains. So if you have 20 subdomains, you can split the original model in 20 subdomains. The speed up will be a factor of 20. And then things get more interesting for large-scale system. Okay, I think time is running short. Maybe I will focus on the computational effort. I skipped some tricks. So let me see. Yeah, here, this is, let me first see the, do I see? Yeah, okay, here, sorry, I have to skip. So here we try to estimate 282 parameters. And the idea is left is the true, and in the middle up is the initial, and then if we do it in a global way with finite difference right, it's really the approach that is the most accurate one. And if we do it in a reduced order domain decomposition methodology, you get the bottom figures, which are, depending on the type of domain decomposition, it looks pretty reasonable. And if you look at the cost function, then it depends on the type of domain decomposition, but they come pretty close to the reference, which are the red lines. And the fact that it is not perfect is because we don't have infinite amount of data to reconstruct it. So, but of course, the major point is the number, the computational effort. I think, yeah, and that's. It took 72 full order simulations to estimate these 282 number of parameters. So it scales pretty well, that if you would have a larger model with more domains, then the number of the computational effort increases because the full order simulation takes more time. But in terms of number of full order model simulations, the computational effort will not increase a lot. So you can estimate 2 times as much parameters with the same number of full order simulations. So it scales reasonably. Okay, and then I've skipped the neural network because of time and jump to the final conclusions. For some problems, we would like to have variational data assimilation, but we would like to have a methodology which does not require the adjoint. Model order reduction in combination with domain decomposition can solve quite a lot of variational data assimilation problem. It scales reasonably well with the number of parameter. And that's domain decomposition where you do everything local. You need a way to avoid discontinuities over the domain. Therefore, we have also a methodology where you introduce the parameter only in the subdomains, but you project it onto global patterns to have smooth global patterns. Okay, and then deep neural network performs also well. I didn't show the results. It's more general and easy to implement, but it's a bit trial and error, and it's less efficient, a little less efficient. But the training, that's really quite a complication that takes a lot of time to get the. Okay, I think, sorry for being 5 minutes too late. And of course, details are available in the papers that we have submitted or have appeared recently. Then the technical details are there with all the numbers, of course.
Well, thank you, Arnold. This is getting literally hot here because of the deep learning and artificial intelligence is getting all over the data assimilation field. Okay, so we have one question from Xiao Dong that sadly now is out taking the kids for something. And he's asking, hi, Arnold, is it correct that deep neural network is also used to learn adjoint information?
No, the deep neural network is you generate model simulations perturbing the parameters to get information about the physics of the forward model, and then you approximate the forward model. But the neural network is easy to derive the adjoint of. So once you have an explicit forward nonlinear representation of the model, then the linearization and the making the adjoint can be done by the code. You don't have to do it yourself, but you have automatic differentiation tools that can handle it. Does this answer the question?
Yeah. Do we have any other question before I ask my own? Gear, Jeff, Elias, go ahead.
So I'm interested, Arnold, in if you actually have multiple minima, how does the reduced order modeling interact with that situation? Can it prefer one minima over another, or generate issues like that?
Yeah, the reduced model act like regularization because you had all kind of tiny little local minima in the original full cost function are kind of removed by by using a reduced model. So so small scale features are removed. So it helps in avoiding that you get caught in a local minima. But of course, the global picture is also it will not come to the exact minimum, but it's not. It helps more than it makes things more complicated.
Great, thanks.
Yes. I lost it a bit because there's a lot of mathematical methods and methodology here. But do you know that what kind of problems you are solving in the end? Can you say that you're actually solving Bayes or a certain formulation of Bayes? Is there a particular, you know what the solution is in the end?
Yeah, so the whole system is optimization. So there's no probabilistic representation. We really see it as an optimization problem that you try to find the minimum. So what do I say?
It's defined in terms of some kind of norm, and that norm, in some cases, you can relate that to Bayes or whatever. But
no, in the final answer, you have so you can converge to the exact 40-var approach if you increase the dimension of reduced model. Then step by step it becomes more and more close to the original formulation. So there is a kind of convergence to the full original problem. But of course, we cannot do this because that's too computationally demanding to do experiments like this. So
okay. I have one final question. How does the method scale with the number of parameters? You explained some of it, but I didn't really get it. But if you have 10,000 parameters, like in the porosity field in a reservoir simulator, would you still be able to use the same method, or?
Well, there is a set. So the computational effort is, or the number of model simulation that you need is the number of parameters in each subdomain multiply with the number of subdomains. So if you have a model that you can reasonably, you can have 100 subdomains, do a domain decomposition with 100 subdomains, and in each subdomain you have 100 parameters, and you have 10,000 parameters, then the computational effort is a few hundred model simulation. It's related to this 100 parameters that you have in each subdomain. So there is a limit. It's not the 40-var like you can do it for a million parameters. So the maximum that we did up to now is 600 or something like that. So in principle, you can go further, but 1,000, I think I would be happy, and above this, then it will be tough.
It's an interesting approach. Thank you.
Well, Elias, do you have any question regarding this application of the joint-free 40-var with machine learning?
Well, we are like doing something similar right now, but we are using just like linear models. So what we do is that we assume that these processes are first order Markovian, and then we split like the time domain in intervals of 6 hours, and then we build propagators from 1 hour to the other, right? So we have like some sort of piecewise function for representing the dynamics of the model in time. So we have like we assume that at each hour we have like a linear model which propagates. So that's basically what we're doing right now. We are trying to explore the deep learning thing as well. So we are pretty sure that we should get like better results. One of my students will present a poster where he will show how we are making use of this idea in the context of data assimilation, how we make use of linear models, piecewise linear models, to propagate model variables from one time to the other one. So it's basically what I want to say. It's a very nice work, Arnold. I mean, it's the correct direction right now, and it's a very nice way to exploit information from the observations to account from the missing dynamics in the numerical model. So it's
okay. Yeah. Thanks. Let's keep in touch. I'm interested in what you are doing there. Yeah.
Well, now we have 30 people watching now, and I think that we approach to a really, as I mentioned, hot topic in terms of how can we use the machine learning and deep learning black box models in order to help the data assimilation process. 2 years ago, I met with Gada from Deltares, and we established a framework for machine learning as a source of organized data for the data assimilation process. The problem that we needed to tackle is trying to get a really good interpolator of the information we're going to use for the data assimilation problem, and at the same time trying to get the data organized to help the process of estimating the PDF. Have you ever thought about it? Because of tomorrow I will try to open my own insights on the field. Do you have any idea on that regard, Arnold? Do you have any plans for the future? Instead of using the black box model for getting a trend, try to use it to organize data and helping the estimation process?
Yeah, you mean merging artificial intelligence with physical information. Is that, yeah?
Yeah.
Yeah. We are working on the kind of, what we tend to mention now, physics-aware artificial intelligence, where you try to build in a priori your conservation laws in the network. But that's in an initial stage. What we up to now did was just generating data from the underlying physical model and then use this to fit the neural network. That's the kind of first step that we did. But we prefer to have physical knowledge in the neural network, that you really add this information to the network. But that's an idea for the future, for us at least.
Well, thank you, Arnold. Professor Sandu, welcome to our workshop. I can see that you already joined us for the next talk. And okay, just to close this session regarding the machine learning for the adjoint free data assimilation, I will mention that tomorrow we're going to have more details on a Colombian application of data fusion, column filtering, machine learning on the pre-conditioning of the data, looking for the data assimilation of a numerical weather forecast model. Professor Sandu, do you have any questions for Professor Hemming?
So just hello, everyone. I've been listening and then teaching and then listening again. So I just now connected to the camera. So just saying hello.
Hi. See you again virtually.
Well, okay, professors, allow me to move forward the next presentation. Now, Elias Niño, my apologies, Arnold. Now we're going to listen to Elias Niño. This is the last by the talk for today. Afterwards, we're going to have a poster session of our students, so please do not leave the workshop. Elias is going to share with us the efficient ensemble-based methods for sequential data assimilation. He is also working with us in our program or research program funded by MinCiencias called Exposure to Pollutants Regional Research. And we are looking forward to see and to learn what he has to show us today. Thank you, Elias. Now, go ahead.
So, no, can you hear me, right?
Yeah, perfect.
Excellent. So, okay. Thank you very much, Olga, for the introduction. So, thanks everyone for watching this presentation. I'm very glad to have all of you here supporting this workshop. So today I'm going to talk about efficient ensemble-based methods for sequential data assimilation. Associate professor in the Department of Computer Science, Universidad Norte in Colombia, and I'm the director of the Applied Math and Computer Science Laboratory in Universidad Norte as well. So this is like the outline. So this is very basic. So we're going to talk first about data assimilation component concepts. I may be going to skip some slides because I think all the previous speakers gave very specific details, so it was in a very nice manner. So we're going to talk about ensemble-based methods, localization methods, shrinkage, covariance matrix estimation, some modified Cholesky decomposition implementations, parallel implementation of the ensemble methods, and some recent references. So this is like applied math. So we work on data assimilation methods, inverse problems, combinatorial optimization, numerical methods. And I want to thank my PhD and master students, specifically Randy Consuegra, Felipe Acevedo, Omar Mejia, Juan Rodriguez, and Andres Movilla. So they are like supporting different ideas, different research directions that we will have the chance to show after my talk. So motivation, weather forecast, and warnings are the most important service provided by the meteorological profession. So we know that, and it's highly useful for government and industry, also to improve efficiency of operations and a lot of things, right? Nowadays, weather forecasting is grounded in scientific principles and methods. So we have seen some of them so far. I make use of advanced technological tools. So just to make use of high performance computing to efficiently implement these methods in practice where we have a large number of variables. So how do we forecast the state of highly nonlinear dynamical system? Well, we saw that we need an imperfect numerical forecast, observation of the actual state, and an observation operator. So basically, we want to track the state of an actual system, which approximately evolves according to some imperfect numerical model. This numerical model, so basically take a state at the current time and then propagate it to a future one. Usually models are given in the form of partial differential equation in space and ordinary differential equations in time. It's like an initial value problem, right? We have noisy observations from the system, and we make some assumptions on the error of those observations. The common assumption is that they are Gaussian. Yeah. We listened that may not, and that's fine as well. And we have an observation operator, which basically relates variables from the state space with observations. We have a prior estimate. This prior estimate comes from an imperfect numerical forecast. So we have a numerical forecast, and we assume that that's the best thing that we have before any observation. So that's our prior estimate. And then we consider errors in the forecast as Gaussian as well, right? So we have like a B, where B is basically the background error covariance matrix, and R is the data error covariance matrix. In our context, model components are in the order of millions, while observations are bounded by 1,000, 100 in some cases. So we have like sparse observational networks once we have processed the observations onto a numerical grid. So components that we have here like an actual state, which is basically a peak A. So we have the observation operator. In this case, I'm assuming that the observation operator is linear. So it's what we're seeing in B. The dark region denotes the observed components. And then we have observation. Y is the peak C. We can see that the noise, so alter the information of observations, and this noise is characterized by many sources, right? We can think in interpolation when we interpolate the observations from the different stations to the numerical grid, but also we can have errors in the observation just by the instrumental errors, right? So the instrument have some errors when take the measurements. And we have XB, where basically XB is the prior estimate, is what the model says. So we can make use of Bayes' theorem. In Bayes' theorem, we combine information from the imperfect numerical model and the observations, and we assume in the two cases in this talk that the sources are Gaussian. The underlying errors distribution of background errors and the underlying errors distribution of observations. So we can easily show that the posterior state, I mean, the state that we obtain once we assimilate the observations, can be computed this manner, right? Where basically here R plus HB, H transpose is commonly called the innovation matrix. So information matrix is the precision. Then we will have a posterior distribution for the vector states where the mode, the mean in this case, is XA. And we have analysis covariance matrix, which is given by the expression that you're seeing in the screen right now, right? How do we estimate XB? Well, as the previous talks, we can make use of ensembles, right? We can make use of ensembles. How did things work in sequential data simulation? Well, sequential data simulation is something like what you're seeing right now, right? So in the peak A, we have a free run in blue, and we have the actual state of the system in red, right? Let's assume that this is any variable. Now we have some assumptions that, for instance, that the system is observable, right? So we have observation of the system. So typically they are given by some radar or satellite radiances. So we have observation of the system in time. And then what we do is that at each observation time, we apply this Bayes formula, which allows us to compute the posterior state based on the observations. And then we employ this XA as our new initial condition for the initial value problem. So we take this analysis state, we put it into the numerical model, and then we propagate the numerical model in such a way that we expect the forecast is valid for some time period. Once we have ready another observation, what we do is that we incorporate the information of that observation in our system. In this manner, we continuously update the state of the system based on observations. Actually, the state of the numerical model, which is actually the forecast. So at the simulation step, we don't need to estimate XB and B, and then we can make use of an ensemble of model realizations. In ensemble of model realizations, what we do is that we have an ensemble of numerical forecasts. With that ensemble of numerical forecasts, we can estimate the empirical moments. I mean, we can employ the empirical moments of ensemble to estimate the population models. In this case, the moments of the background errors distribution. The background state can be estimated via the ensemble mean, while the background error covariance matrix can be estimated via the ensemble covariance. Delta X is given by the anomalies, where basically we subtract the ensemble mean from each ensemble member. Now, it's very important to understand that in practice, numerical models can be quite chaotic, right? So we have a very known model in the context of data simulation. The Lorentz 96 model is a very nice tool for testing, emerging data simulation methods, to try methods. And it's very interesting because it's highly chaotic when the external force is set to 8. In this case, we're working with the Lorentz 96, and the number of variables is 40. So we can see that small perturbations in the initial condition, they grow very fast in time, right? Because the model is chaotic. Of course, errors don't grow in the same magnitude in all directions. So there are some directions we develop more errors more quickly. They amplify errors, others not. So in this case, I'm going to show you the variables 5, 10, 20, 30, 35, and 40. So you can see that how errors are, how propagations, how small perturbations propagate in time, how they are amplified by the chaotic behavior of the system. So I can make use of 10 to the 5 ensemble members, and then I can estimate the background error covariance matrix B. This will tell us how errors in different components are correlated. And of course, it can help us to update errors or to update components based on the information of observations. So this is very nice, and then we can, make some assimilation with that information. If we think in the stochastic ensemble Kalman filter, well, this is like an extension of what you saw before. I'm making use now of an ensemble of model realizations. In the ensemble Kalman filter, what we do is that we basically update the stochastic version. We update each ensemble member by using a synthetic observation. So in this case, we make the filter statistically consistent, but of course, it can induce extra sampling errors. In this case, we have a matrix delta Y, where basically each column is given by some synthetic observation minus the ensemble member in place. Synthetic observation, of course, are consistent with the data error distribution. So the assumption that we're doing and the moments are employed to build these extra observations. In this way, we also avoid that the ensemble collapse into a single point, because we need to think that in such way, the ensemble members, they span a space, and if they span space and the observation is not in that space, so we will look for the closest point in the space that is the point in the space that is closest to the observation. If we don't perturb the observation, so all of them will try to get to the same point, so we lose statistical information. So this is a manner to preserve the statistical ensemble across different assimilation steps. So we can perform some simulation. Here we are using 50% of observation, so the state vector, so we are using 20. We're observing 20 variables in the peak A and the total number of variables in the peak B. And what you are seeing in the Y component is nothing but the MSE, mean square error at each assimilation time, the L2 error. The point here is that, yeah, we are doing like a very great job, but we are making use of many ensemble members, so the ensemble size is very large. And then we just need to remove some ensembles. So let's do the same thing with 10 ensemble members. We get something like this. And this is because the sampling error is impacting the quality of background error correlations. And that's happened because we don't have like enough degrees of freedom to span the full model space. So in such way, we need to try to extract the implicit information that we have in the ensemble covariance matrix, for instance, the ensemble moments. So we can make use of localization to avoid the impact of spurious correlations. Also, is correctly set up, we can increase the rank of PV. And there are many different flavors, right? We have covariance matrix localization, precision localization, spatial domain localization, and observation localization. So Jeffrey Anderson is one of who works in observation localization. Also, we have in this case, Arnold working on spatial domain localization and building these local reduced order models. And in this case, Adrian Sandu and I work on precision localization. So covariance matrix localization, we basically impose a desired structure on the sample covariance matrix. We define the structure as a decorrelation matrix, which basically mitigates actually decorrelates the components or the error in component with regard to their distances. So the larger the distance, we assume that they should not be correlated. And this, yeah, I know that we can give a discussion in that direction because that's depending on other things, right? But basically, the main idea behind these approaches is to decorrelate components with regard to the physical distance or some consistent norm. So in this way, for instance, I'm showing you the ensemble covariance matrix, the desired structure, and in C, the resulting estimator. The same for D, E, and F, okay? So we have some experiments and we can see that results are improved for 100% of model components, the total number of model components. And also we see that there are other results for 50% of model components. For instance, in figure F, there are other topics such as covariance matrix inflation. Maybe it requires covariance matrix inflation for improving the results. Precision matrix localization, what we do is that we exploit the fact that when two model components are conditionally independent, their corresponding entry in the precision covariance matrix is 0, right? So the conditional independence is given by some radius of influence. So I have a numerical grid. In this numerical grid, I associate points by some local box. This local box is given by a radius of influence. You can think in local boxes formed, for instance, by the local ensemble transform Kalman filter. This idea is exploited in the local ensemble transform Kalman filter context to avoid the impact of spurious correlations. That's basically what we do. And then making use of this idea, we make use of, we propose a modified Chebyshev decomposition. Actually, we make use of the modified Chebyshev decomposition in the context of data assimilation. The modified Chebyshev decomposition was proposed by Michel and Levina. In this case, we build a local box for each model component, right? So for each model component, we build a local box. And then depending on the label of model components, on that label, we choose the predecessors, right? So the predecessors correspond to those model components whose label is lesser than the point in which we are computing the entries of the precision covariance matrix. So basically, we're fitting models of this form, accounting only for the predecessors of each model component. So here we have an example. So we have PV, this is an ensemble covariance matrix. What we do is that we choose some radius of influence. This is for the Lorentz 96 model. You can see the structures T and D. You can see the resulting structure in B hat inverse. This is our estimate of the precision matrix of background error. And then we have the estimate. You can see the surface, and then we invert the estimate. You can see B hat. It looks like a localized covariance matrix. I remember when I was a PhD student in Virginia, I think I was discussing with Dr. Sando about maybe how to prove the relation between the localization radius in the inverse space and the localization radius in the space, right? So that's an idea that is around. And something that we can see here is that the desired structure in B hat inverse is given by the structure in T. So actually you need to define only T. This is very important because in this manner you can avoid the use of a lot of computational resources, computational storage, because all you need to represent V inverse is T and D. D as a diagonal matrix, and T is nothing but a lower triangular matrix, and it's lower triangular matrix because we are ensuring that in the regression coefficients, only the predecessor within some local box are accounted for computing those coefficients, okay? So that's very, very, very encouraging to exploit in the actual context. So right now we are just working, making use of some real information. That's an ongoing work. Some of my students will talk about that later. So here we have the precision matrix localization. The results are quite similar to those that we saw when the localization matrix is employed. And then the fantastic thing here is that we just don't have a very nice representation of the inverse precision matrix, but also we can exploit that special structure to come up with efficient implementation of the ensemble Kalman filter for very large system, right? So system with a lot of variables. So in this manner, we can like decompose the precision matrix. This is like the H transpose R inverse H, Z times Z transpose. We can build this as a sum of other products, and the point of doing this is that I start with my V inverse, right? This is V hat inverse. numbers. This is my estimate of the precision matrix in the form of T and D. And what is very interesting that we can make use of, for each observation, we inject that information in the precision matrix, right? So I start with the precision matrix. I have information of the observations, and then for each, I take each observation, and then I inject the information in the structure of T, of, in this case, V inverse. And at the end of the day, when we go all the way to the number of observations that we have, we end up with the structure, or let's say decomposition of the precision matrix of posterior errors in the same form, right? T transpose D T. So this is very nice because in some way I have like the posterior precision matrix, or precision matrix of posterior errors. That's what we have here. And given the special structure, of course, we can exploit that to develop an efficient manner to assimilate observations. Well, this is some math where basically I show how to develop the equations to update the Chalecki factor based on the rank 1 updates. Actually, you can do this in a rank 1 update fashion. Also, you can develop a rank n update. The very important thing here is that we don't need to build the V inverse matrix to get the posterior factors. What we do is that we update the prior factors, making use of observations. In this manner, we end up with the posterior factors in the same way, in the same structure that the prior ones. So the posterior L still being a lower triangular matrix, and D, well, is a diagonal matrix as well. Also, this work was with Dr. Sando when I was a PhD student in Virginia Tech. I worked on shrinkage covariance matrix estimation, where basically we combine information from the ensemble covariance, and then we use the prior information. So our prior is that basically the model components are not correlated. So that's why we assume that the prior is the identity times some variables, like just having the variance, right? It's the average of the variances. And then this is our prior, and then we have the ensemble covariance with additional information, and then we combine those sources of information of what we think is the structure, and then we let the ensemble covariance to say, well, you are assuming that it's a diagonal matrix, but I'm saying another thing, right? So in that manner, we develop this ensemble. What is very interesting in shrinkage covariance matrix estimation is that they have been proven to be more accurate than the sample covariance matrix, of course. Better condition than the true covariance matrix. And they are strong under the condition having more variables than number of samples, which is actually the context in which we move. So we have many estimators. So we have like the Ledoyan-Wolf estimator, Rao-Blackwell Ledoyan-Wolf estimator, and it's proven that under Gaussian assumption, the Rao-Blackwell is much better than just the Ledoyan-Wolf estimator because of the Rao-Blackwell theorem, right? So for here, what we do is that we replace PV by a better estimation of B. So RBLW is the estimator of the Rao-Blackwell Ledoyan-Wolf in the ensemble common filter context. So here, basically, we estimate some parameters. But the direct implementation is prohibitive. In that moment, we decide to exploit the fact that the trace of PB and the trace of PB squared can be computed based on the matrix of member deviations. So these save a lot of computational resource. In this manner, we can develop equations that looks like this. Mu B hat is nothing but just the sum of n-1 singular values, and gamma V hat is the equation that you see there, right? But what is very interesting here is that we never compute PV, nor this full singular variable composition, because delta X is a low rank matrix. It's a actually rectangular matrix where we have more variables than number of ensemble members, so the computational cost is very economic, right? We are talking about n squared, where n is the number of ensemble members, so ensemble members is squared times the dimension of the model state. So basically, it's linear with regard to the dimension of the model state, and since the number of ensemble members is very small with regard to the dimension of the vector state, we are good, right? So in this manner, we can propose the ensemble common filter in the model space. In that moment, we also propose the ensemble common filter onto the ensemble space. I'm showing you here just the version in the model space, which basically everything end up with the solution of a linear system, which can be performed by making use of the iterative Sherman-Morrison formula. It's another direct method to solve linear system in the context of sequential data assimilation, specifically in the context of the ensemble common filter. We make use of some experiments with the SPIDI model. The SPIDI model is an atmospheric general circulation model. We choose the T63 resolution. It's 96 times 192 model variables, 4 variables. We had 8 layers per variable, so we are talking about 590,000 of model components. No, actually, it's 59,000. No, 409,000, yeah. We have 3 sparse observational networks where we distribute observations. And of course, we compare the results with the local ensemble transform common filter, which is a very well-known method in the context of data assimilation. And it's employed also in operational contexts. And Fortran 90 was like in this case, the computational language that we use for making use of implementation. So we have like 3 observational networks here for different number of observed components. So the largest P is 12%. So it's a very small number of observations that we have with regard to the actual dimension of the model state. And then we have some results here for the background, the modified Chalic decomposition and the LTKF. I let like the inflation fixed. So yeah, I'm pretty sure that maybe the LTKF results can be improved by making use of a different inflation factor. But since I have many variables to deal with, and this numerical model is not that cheap for the chosen resolution, so I just set up a single variable. We can see that in these 2 cases, for the radius of influence 3 and a radius of influence 5, well, we perform better under these scenarios and this configuration. This is like a snapshot. The point A is the reference, that's the reference solution. We have the background. We have some spurious waves near the poles. And then we have the results from the modified Chalic decomposition and LTKF. In both cases, we can see that these methods are able to reproduce the actual contours, the actual shapes from the reference solution, but the scale in the LTKF is quite shifted. So in this case, we get that better results. This is for the 5th layer of the meridional wind component. Also, we do this for all variables. This is, for instance, some peaks from the 2nd layer of the zonal wind component. And this is like the local estimation of V inverse looks like, right? So we have like 4 variables. And then if I just consider a local box, and then I focus on that local box, I can see that the spatial structure is given by, for instance, the number of variables and the lower triangular matrix. So again, I have a lower triangular matrix here. It looks like what you're seeing in A. This is how the precision matrix for the SPIDI model for a local neighborhood looks like. So I just forget about the entire domain. I just take some samples across all ensemble members of a local box, and then I make this plot just to have a clear picture of how the general convergence matrix look like. And then you can see again that the desired structure in B inverse is given by just the structure of T. I mean, whatever you have in T, you know that T transpose T will give you the structure of the matrix. Of course, the estimator is T transpose T inverse T. Here, I'm just telling you that if you desire a structure in V hat inverse, what you need to do is to specify the structure of T. And then in C and D, I'm showing you the surface of the precision covariance matrix. No, actually in C and D, I'm showing you the inverse of the V hat inverse. So I'm showing you how the V estimate looks like. I mean, I never computed. I just did it for having a clear picture about what's going on, how the estimator in the model space looks like, and then you can see how it's right. So it makes some sense in the direction that we have blocks. So each block corresponds to a variable, and this is the specific humidity, which is lesser in magnitude than the other ones: U, V, temperatures, and the specific humidity. So this is how the B hat looks like. We have also the estimate with the Rao-Blackwell, Ledoy, and Wolf covariance matrix estimation. This is the results. This is how the Schrinker covariance methods looks like. So we compare the results again with the LTKF. The localization in the context of these Schrinker covariance matrix estimators is similar to that to the LTKF, right? So basically, we just set up some local boxes for each model component with regard to observations, and then we employ all the information that we have within those local boxes to update model components. So we have like an accuracy, in this case, reference, again, background, the RBLW, and the LTKF. So that's what we have. Also, we have, for the second layer of zonal wing component, we have some snapshots there. You can see how the RBLW can, reproduce the reference solution up to some accuracy, of course. Then there is a point, right? The point is that we cannot just make use of these methods without thinking in HPC, because, well, we need to understand that we have large vector states, and we have observation. I mean, just the preprocessing of observation is a big deal. I'm currently working on that. Yes, just to take the METAR files from different stations. So one of my students will talk about that as well. Just collect the METAR files, to read those files, then to average observations with that falls in the same point of the numerical grid. There are many things to do there. There is a very, very nice, let's say, that work from the scientific perception, a nice work to do with the observations before we employ in the context of data assimilation. That also demands computational resources. But here I'm talking just about the moment in which we have the observation ready, and then we perform the assimilation step. So just for doing that, we also need supercomputers, right? In this case, we make use of the Blue Ridge supercomputer at Virginia Tech. It was, again, a work done with Dr. Sandu and Xinwei Deng from Virginia Tech. In this case, we make use of Blue Ridge. This is the name of the supercomputer, right? Blue Ridge is, well, we have like a lot of cores here. Then the methods are called in Fortran using MPI. And then we need to, in general, well, if we want like to speed up algebraic computation, I'm not talking about speed up in the sense that HPC, but just speed up in the best way with which we can perform the matrix computations. We make use of LAPACK and BLAST, and in this manner we can perform efficiently the matrix computations. And then we vary the number of processors from 96, so we make use of 16 computing nodes, to 2048 processors, so 128 computing nodes in our cluster. What we do is, of course, we make use in this case of domain decomposition. So we have the domain, and depending on the number of processors that we have, we just decompose the domain, and we send each subdomain to a different processor. In that moment, we try to preserve the physics by just not sending the information of the boundary itself, but also, sorry, not the local box itself, but also the boundary. So we send the local boxes, and also we send part of the local boundaries. So the boundaries. In this manner, we try to not isolate each local box, but to give to each local box information of its neighborhood of domains, right? Of course, we think that there is another way in which we can exploit this HPC nowadays, right? And then we can build optimization problems in which we enforce the transition between local boxes belonging to a same neighborhood, right? The width of each of those local, this case, local boxes and their corresponding domain and their corresponding information of the boundaries are given by a radius of influence. So the larger the radius of influence, the larger the information of the boundary. So we make use of, as I say, 96 processors, so 16 computing nodes to 2048, 128 computing nodes. And we have here different results. We show for each method the number of computing nodes that we use. So this times 16 gives you the number of processors, the total number of processors. So we can see that, well, the accuracy here is still the same one, right? So the results are better than the LTKF. Again, I'm pretty sure that we can do something additional to improve the result of the LTKF, but what I want to show you here is that the LTKF results don't change for a very simple reason. That you don't see variations of the results across different domain decomposition. Is because the LTKF is a deterministic filter, right? So we don't make use of synthetic observations. So we reproduce the results regardless the number of domain in which we decompose the global domain, right? On the other hand, for the ENKFMC, we split the domain, then we build some synthetic data. I mean, I have the same observations. We preserve this scenario, we reproduce the conditions, the scenario, etc. But we need to build synthetic data at each observation. When we build the synthetic data for each domain, subdomain at the different processors, we make use of the processor ID. So we are not able to reproduce the synthetic data. And then that's why you see these small variations here, right? I mean, you can see that in average, the performance is very good. But you have this additional thing, right? Because we cannot reproduce the synthetic data at different processors because this synthetic data depends on the processor ID. Of course, we can just build a very large amount of synthetic data and then send it, but that's not the way in which we will proceed in practice, right? So this is for the specific humidity we have for the zonal wind component. We have also for the RBLW, same story, is a stochastic filter, and you will see small variations in the results. Also here we can see for the specific humidity. And then we have the time. We didn't compute the speedups at that moment. That was in a different paper, in which the number of processors, again, the range. And we can see that the LTKF is much faster. Actually, it should employ a log scale here. But well, what I want to say here is that you can see that, of course, the LTKF will perform much faster because in such way, it depends only on the local domain. I compute the ensemble covariance and proceed, right? In the other two cases, for the modified Chalecki decomposition method and also for the shrinkage covariance matrix estimator, we need to make use of covariance matrix estimation in general. That's an additional time, which can be exploited as well onto different processors. So and therefore that's what we see here. As we move forward, or as we increase the number of computing nodes, we see that the computational time of the analysis step can be reduced, basically, can be reduced. We have some ensemble common filter modified Cholecki publications. So as I say, I have a work with Adrian Sandu and Singwen Wei, from Virginia Tech. That's in Science Journal of Scientific Computing. And also we have the parallel version in Journal of Computational Science, Elsevier. Also, we have this efficient implementation of shrink and covariance matrix estimation in cluster computing, Springer. Well, I have another publications there with some colleagues from Argonne National Lab. Right now, it's in Lawrence, Livermore, but Cosmin Petra, Victor Zavala, Mihai and Itescu, they were in Argonne National Lab when we were working on this paper. And also we have ensemble common filter implementations based on shrink and covariance matrix estimation in ocean dynamics from Springer. Well, this is the bibliography I use for the talk. And well, that's it.
Well, thanks, Elia, for your presentation. That was a really amazing work. And I'll invite the Professor Anderson and all the people that is in the room for some questions. Professor Sandu, please turn on your camera. Professor Anderson. Please go ahead.
Thank you for the nice presentation, Elias.
Thank you, Alexander.
Well, we have a question from Amit. So I'm surprised he's not here in the room for asking the question himself. But he's asking qualitatively, how different is precision matrix localization versus running localized computations with subsets of data?
What is the question again? Sorry, I didn't get it.
Asking, could you, Laura, please? Yeah.
Okay. Okay. Well, I think that's a very good question. So when I run experiments, as I show you, we didn't see like any significant difference. But of course, that can depend also in the dynamics that we are targeting, right? So we were working U and V model components, so the wind model wind components, the temperature, the specific humidity, right? In that scenario, we didn't see like any changes when we decompose the domain and then we compute the local domains as when we make use of the entire domain. So results were very similar, and the discrepancy is given by the fact that we make use of synthetic observations into the local domains. So based on the experiments, of course, I should need like to maybe work a little bit in the theoretical part, but just based on the current results, I don't see like any huge difference. I mean, the precision of the estimation is not impacted by just using the entire precision matrix or the local domain, right?
Thanks, Elias.
Thanks.
So we already have a question. Well, Elias, I'm interested into a more high resolution applications of your technique because as you may know, the speedy model is not enough for Colombia, and we need to tackle more problems in trying to get into a more complex dynamics with different not only different domain localization, but also different physics scheme. What do you have in mind for our Colombian problems or the models application that we already have under our wing?
Yeah, we are moving right now to make use of this modified liquid decomposition in an operational environment. Right now, we are working a very large scale by using the speedy model, right? And actual informations from different stations around the world to update the background state, the forecast. Results so far are very good in the sense that we get closer to the observations that all what we have when we make use of real data, right? So we don't have like a reference state, and then we need to compare it against observations. Since we are working in a regularized scenario where we have a prior estimate and also we have each of the correlations regularized as well, we expect not to overfit in the observations. So we are trying like to leave out a certain set of observations to compare with. Results are quite interesting so far. Also, we are thinking to mix information from the speedy model, which is a very coarse grid, with that from maybe a machine learning model. We have like this the National Oceanography Administration from the US, and also I think Jeffrey Anderson knows about it. They have like a huge data sets, right? So they have information starting 1979. So we can like build numerical, basically machine learning models, which can encapsulate all this data. The good point with that is that resolution is very high. So we have like a very high resolution with information in the NOAA datasets. And then we have this coarse grid, and then we can just make simulations with the speedy model. We can run simulations with a machine learning based model, and then we can take these the coarse grid with the finer one to combine the information. Then maybe we can describe better the information in Colombia with a finer grid, right? So the numerical model will still be a coarse grid, but if we can correlate the way how this speedy model propagates the dynamics and how the machine learning propagates the dynamics, we can get something like finer resolution results, right? We can improve the result. Not improve, we can see, especially speaking, we can see more information in different points.
Thanks, Elias. Do we have more questions? Because if not, I will move to a quite spicy one. You propose an efficient ensemble-based methods for sequential data assimilation. What happens if we needed to assimilate vertical data? What if I decided to move towards a crazy experiment, getting some sensors into a helicopter and fly the entire country? What would you propose to have this data assimilated? Is this possible in your scheme for the atmospheric modeling problem?
Well, that will be like a very good news for me, right? Because actually, what we're using like just the meta files around the world, and the best thing that we get is, I think, the observations up to 3,000 or 5,000 meters. So we cannot go beyond that, and then we assimilate only like the first 3 layers of the speedy models. For instance, we don't have information in the other altitudes. So if you can give me those observations, that will be like very beneficial for me, right? Because I will have extra information in the other layers. That's why we make use of these machine learning models. I mean, I don't want you to think that I want to replace the physical model by a machine learning one. No, that's not what I want to do. But my point is that, physical models are imperfect because we can't not represent the reality in the machine as is. That's not possible, right? And then we make use of some physics simplifications as well to make it, computational feasible. That's fine. But my point is that if we can introduce the missing physics, if we can make use of past observations to take that information and encapsulate into the numerical model, my point is that we can reduce the impact of the unspecified physics by the information encapsulated in observations. So since my point is that we can maybe improve the result of the numerical model because the missing physics can be fed or can be injected by the historical information contained in the observations. So we have more than 4 decades of observations. So my point that that information encapsulates a lot of physics and dynamics from the actual state, right? So if we can put it into the numerical forecast in such way, I'm pretty sure we can do a much better work. And if you are giving more information across different numerical layers, that will be fine as well. Oh, we can't hear you, Olga. Your mic. The microphone, yeah. Okay.
Sorry. Professor Anderson, Professor Hemming, Professor Sandu, do you have any question? We have a question from Daladier Hava, Professor Hava. How much the scientific data does affect your model?
Well, that's a very good question, Daladier. I'm pretty sure you're talking about the model, the machinery, the Bayesian model, the Bayesian framework. Well, the point here is that the amount of synthetic data is given to the ensemble members that we have. So that's a first thing, right? And in practice, in operational scenarios, and also Jeffrey Anderson and also Arnold have known about this. They work very well, right? So they encapsulates, actually they serve the dynamics, the statistics, sorry, of the ensemble. So it's something that's very good and helps you to represent uncertainties. It's good. So in my case, I didn't see like any negative effects, even now that we are working with real data. We don't have, I didn't present any results. That's most of my presentation. The work presented there was done with Dr. Sandu, who is here. We have some preliminary results with the actual data, and they look very well even when I make use of synthetic observations from the real data. I mean, just for computing the posterior ensemble members.
Right, thank you. Amit, someone in the room that wants to ask a question to Professor Niño?
Amit is here. Okay.
I assume that, yeah, but you have another question from Daladier also, which is the next step with your research.
Well, the next step is I think there are two directions, right? The first one is how can we exploit years of information to get insights about very tough things in current scenarios. For instance, how can make use of years of information to develop adjoint models efficiently, and then to incorporate those adjoint models, making use of numerical models. Also, how can we, and I think is extremely important, to reduce or to decrease the uncertainty of model errors by injecting information of historical data. So we have uncertainties in models, and those basically comes from some of the things I said before, right? So, for example, when we simplify physics, or maybe we don't know completely the system, so we can make use of the implicit data in this historical information to feed the model with additional directions, which comes from the reality, right? So I think and also I think it's like a two-way directions, right? Commensalism, where we have a numerical model, I have a machine learning model, this propagates, I have states, I combine or I augment the state, I compute correlations, and then I can adjust the numerical model by the implicit dynamics or the hidden dynamics in my data. And also I can inject the dynamics from the numerical model in the dynamics of the machine learning model, for instance. So it's some ideas that we are working right now. It's not a completed work, and we are working in the theoretical part and see how we can develop this idea in a very efficient way, in practical way as well.
Well, yeah, because I'm getting concerned about the operationality of that kind of formulation. Well, I'll take the advantage in order to communicate that as a group, we are going to have during our exposure to pollutants regional research plan, we're going to run a mission jointly with the Colombian Air Force, and it's going to be called the Helicopter in Situ Pollution Acquisition Experiment 2, because of last year we made it in March, and we're going to try to run the experiment in November. What we are going to do is that we're going to fly an aircraft, like a helicopter, from the Colombian Air Force, and we are going to put some instruments on top of the helicopter in order to get some measurements of gas and pollutants concentration with different instruments that the team from the Universidad CES, Universidad EAFIT, and Universidad Uninorte, Universidad de Antioquia, and EAFIT jointly want to test. And of course, we're going to get the chance to establish a different way to get some data in order to get into an operational model. Happily, this will be something recurrent on time, depending on the technology that the Simple Space spin-off from Universidad EAFIT has been working on. And I'd love to try to remind you that we already have a twin workshop that was like 1 month ago, and they plan the mission, they work with the instruments, they help us a lot. And from one side, we work in the theoretical framework. From the other side, we work in the operational setup. And from the other side, we're working on getting the instruments ready for helping together to know more about our airspace and jointly try to provide the society good results in order to improve the Colombian scientific and technological development. Well, I would like to thank you all for joining the workshop, but I want to invite the students for the poster session. What we are going to do, hi Miriam, is to have our students sharing their results, and that's good to have a very important people in the field watching the development of the Colombian students, of the Colombian researchers. I want to thank all the people from Norway, from the Netherlands, from Japan that joined us, and some of you that are not mathematicians or engineers and wanted to know more about what we do in order to get the country move forward towards the science. Well, tomorrow we're going to have the second day. We are going to be chaired by Elias, and tomorrow we're going to have a lot of talks about the operational setup and how we know about our country, how we use the data that we already have available from satellite, from surface, from a radar. We're going to talk about new theoretical developments inspired in our own dynamics. Because as Professor Anderson mentioned, sometimes we use our understanding of the world in order to develop mathematics, and sometimes it's backwards. Well, thank you very much. We're going to take 3 minutes time in order to set up the poster sessions, and thank you very much.
I want to, well, just to reinforce what you said, Olga, with regard to the schedule tomorrow. So we have we start with Bayesian estimation and artificial intelligence as the source for uncertainty reduction for decision makings is given by Professor Olga Quintero. It's 8:40 a.m. Then we have an invited talk, multi-fidelity ensemble common filtering with reduced orders control variates. It's Andrei Popov, Chan Hong Mo, Trajan Iliescu, and Adrian Sandu from Virginia Tech. We will have then radar data simulation effects on decision making for operational work model for the Colombian Air Force. Cáceres Richard from the Colombian Air Force. Systematic evaluation of the operational 3D bar work model in Colombia Air Force will be 10:45, 11:15. Andres Yarce and Soto Chica M. And then we will have our last presentation, Shrinker Ensemble for State Estimation, Santiago Lopez from Universidad de FIT and Universidad de Lod. And then we will have the closing remarks. So that's basically what we have tomorrow.
Well, today we're going to have 4 posters. The first one is going to be called Operational Data Assimilation via Modified Cholesky Decomposition. This is a work in progress by Randy Consuegra and Sebastián Racedo. The second is going to be Multiprocessing Fetch of Meteorological Aerodrome Reports from Omar Mejia and Juan Rodriguez. And the third is going to be Learning Toolbooks for Data Assimilation. This is also a work in progress from Andrés Movilla. And the fourth is going to be the first order Markovian model for weather forecast from Felipe Acevedo. This is more or less what we're going to have in the next 30 minutes. All of them are students from Uninorte, and I'm very pleased to have them online. I hope you enjoyed, and I'll be here trying to sharing this session. Well, thank you. Please do not turn on your computer. Stay there for the students.
Okay.
Okay, give me just a second, please. I'm gonna share my screen. Okay. Okay, now I'm sharing.
Well, so hi everyone again. This is our first poster presentation by Randy Consuegra. So Randy, as Olga said, we are pleased to have you here. Please go ahead.
Well, first of all, thank you all for this opportunity to be here and show you some advance in my research. As you can see, my research topic is operational data simulation via modified Cholesky. The composition is a work in progress. Sebastián Racedo and me are working on this area, guided by the Professor Elias Niño. So, as you know, we have many sources of information. One might be a mathematical numerical model, an imperfect numerical model, and such as it propagates some state in time, and we have some observations coming from radar sensors, some sources which can and almost always have some noise. So we want to estimate the next optimal state, the best state, using those sources of information. In a Bayesian scheme, we want to calculate a posterior probability given the prior and the likelihood of the information we have at the observation. So the analysis equation can be computed at the argument maximization of the posterior probability. And given the Gaussian assumption, we can compute the analysis with that equation, as we already know. So in this proposal, making use of modified Cholesky implementation, we want to set up an operational data simulation scheme taking observation from the NOAA, the National Oceanographic and Atmospheric Administration, interpolated to the speedy model resolution in order to propagate it, and using real observation coming from the OGMET repository. That information, I'm going to talk about that later on. So, how was the data processing made? We downloaded the data from the NOAA Reanalysis 2 dataset, which the resolution is 2.5 degrees by 2.5 degrees. It has 144 points, 70 layers, and the speedy model resolution at 330, and it had a resolution of 96 by 48 and 7 layers. So in order to interpolate it, we did not interpolate vertically, as the speedy model has the same levels as the NOAA, but we interpolate horizontally in the dataset using nearest neighborhood and smoother based on nearest neighborhood. We downloaded data from 2020, the 1st of January, until August 24. You can see the resolution of the NOAA resolution and the speedy resolution. This is a little bit the speedy model is bigger resolution. I mean, it takes more area than the NOAA resolution. That was the first thing we had to take advantage of. We did the interpolation in order to do the assimilation. And given the modified Cholesky that the Professor Elias explained before, we imposed a structure on the covariance matrix of the observations. We imposed the structure as we wanted, and we propagated them. And using the real observations, we did a one-step assimilation. I had to remember you, this is a work in progress. We were working with real observations, and observation coming from the NOAA mapped to the speedy. Once the one simulation step finished, we tested as many ready values as ready 1, radius 3, radius 5, radius 7. You can see the errors for the various radio values from the 2 layers. As the Professor Elias stated before, the real observations we had only allowed us to assimilate the first 3 layers, or the layers nearest to the ground, the 925, the 850, and the 700 pressure levels. You can see how the errors evolve given the many ready values. Now we are working on the connection of our assimilation scheme and the speedy model in order to propagate it automatically and do the simulation in a time window. We want to propagate it 1 month and check how the error evolves in time. So right now, this is what our work has led us using a modified Cholesky implementation with many ready one-step assimilation with NOAA data and real observations. What we want to do next is parallelize this implementation even more. We want to change the speedy model in order to use the WRF model. We are working in that direction using the HPC computer that Universidad del Norte allows us to use. So, thank you very much. This is a brief introduction of our work, really fast and really brief. I'm open to your question or your comments.
We're moving forward towards our applications and the model we're using right now. Professors and the public, do you have any question for Randy? Well, if not, please, Juan, join us for presenting your work. It is called multiprocessing fetch of meteorological aerodrome reports.
Okay, can you hear me?
Yes,
Yes.
perfect.
Okay, so let me see. Right. Yeah, it's working the screen. Yeah. So okay. Good morning, everyone. This is our work in progress about this program that allows us to fetch this all information. So let's start with the abstract. A little brief introduction about what we are doing. We are getting all the broad data from the sensors for all the known available stations. And the key, the difference between do that also just fetching the NOAA observations list that they have in the web page, just using our scrapper or something like that, is that we don't want to use data that was processed in another model in order to improve our own models. So the main key here is is fetch these raw data. So how we organize that? So the methodology is pretty simple. We first list all the stations. Also for this station, we have a couple of observations based on the time intervals that we were fetching. So we need to process the methods and also process the data in order to encapsulate it in a data frame that allows us to consume this data in different grids. For example, we have in these results the grids for the Spirit motor and then NOAA motor. So we do that using the Uninorte high performance computer cluster because we fetch 9 million of observations in for the last 2 months. So was really difficult to use that using another services like Google Colab, for example, because we require a lot of time and also require a lot of memory to be process these data. So talking about more deep about the extraction of data, we use open source list maintained by this professor. Is the University of Corral. I don't remember as well. Okay, but yeah, it's an open source list that have all the coordinates, also the elevation and another metadata for each station. This is a screenshot for this list. And for each of one, we fetch the last observations using OEMET, that is another open source platform that allows us to get this all historical information, because we can fetch directly for NOAA as well, the raw data, but it's only the last report. And OEMET have these historical reports. For example, in our example that we have here, this screenshot that we want to show, we use the last 2 months. So we need to exactly go to OEMET and fetch this data. So then we process observations. Omar, I don't know if you want to talk about this process.
Yes. Hello. Well, we organize the information, getting the latitude, longitude, and elevation. We have the daytime that the report was made. In this report, we have the METAR with the help of a library that is METAR Python. We make the process to convert the METAR to the observation of the variables. In this case, we have the station, the time, the temperature in Celsius, dew point in Celsius 2, the direction of the wind and the velocity, the pressure in millibars. After that, we organize the information, but we made we convert the value of the temperature into from Celsius to Kelvin in dew point 2, and we calculate the components U and B of the wine, and the pressure is parsed to hectopascal. We organize the information how is showing in these pictures. We have the daytime exactly, latitude, longitude, elevation, the variable air, who is the temperature, the U wine, B wine, the pressure, the specific humidity. That's the data what we have in the final. After that, we show the results of the 0, 6, 12, and 18 hours. Almost 1,600,000 observation, almost like 9 million observations in all the 2 months. Finally, we store this data in CSV files in the format specified, and that's the oldest station in all the time around the world. That is the active station in the 2 months. The NOAA and Speedy Grid for this information, for this data. In the future, our conclusion, our future projects is to use this method, this program, who is in progress, to make a API who all person can go and get the information and make data simulation in real time, getting the information of OGMED in real time. Thank you. That is our brief presentation.
So, any questions or?
Thank you very much, professors and the attendants. Do you have any question for the students?
So this is Jeff. I just have a question about data sources. So when we do real-time data assimilation projects like this,
not from the NOAA, but more from the Colombian Air Force working on the model. Thank you very much. The next poster is called the Learning Toolbox for Data Assimilation.
Olga.
Andres, go ahead.
There is a question from Jeff Anderson was speaking.
From Jeff?
Yes. So can you hear me?
Yes.
Yeah.
We can hear you.
Right. So my question was, when we do real-time data assimilation with lots of people, we actually get our observations from MADIS, MADIS, the Meteorological Analysis Data Ingest System, which NOAA runs. Have you looked at that as a source for getting this? I think it may be more comprehensive than the sources you're using.
Okay, not yet. Yeah, we are looking for another possible source of data, but now this is our first implementation, because we just want to try first how to code all of that, and also code the application that we are served as a real-time API. But yet we are still looking for another data sources that could be very useful. Yeah.
So I suggest you try MADIS, because it has not only the MEDARs, but it has various mesonets. It's got all the upper air observations. It's got everything except satellite remote sensing. So, anyway, it's worth taking a look at what they have there, and it's definitely accessible to you.
Well, thank you very much. I assume that we can merge all the information we already have available. So after this workshop, everybody will be connected and we'll work together, right? Okay, Andres, we're all yours. A learning toolbox for data assimilation.
Hello, can you hear me?
Yes.
Okay. I'm sharing my screen.
You can see
So
it. Go ahead.
we're presenting a learning toolbox for data assimilation. This is a work in progress between Nasira Maya, myself, and our advisor, Elias Niño. For starters, we have developed like a software that facilitates the teaching and understanding process of the different moving parts of the data assimilation process, like the model and the analysis. We made this by applying a object-oriented programming paradigm, which made us like make an abstraction of the models and the analyses that can be seen in the software, and that allows for a more generalized view of both the models and the analyses that will then allow students or teachers to better explain or better understand different models and different analysis by looking at the new or different ones from the point of view of one that is already known. We also allow in this software to output graphs like the ones shown here that can even better allow for the understanding of the data assimilation techniques and processes. We hope that this software will make this field, the data assimilation processing field, that is an active research, to extend even more than it is right now. I don't know if there are questions or comments or.
I want to be sure that everybody is on camera in order to see them all. Well, Jeff has a question.
I just have a quick comment. I think this is really nice work. I like your examples of your output graphics. The ensemble projection is really nice. You talked about adding new models. So in our data assimilation facility, DART, we have a number of low order models that have just been coded out and checked. So they're in Yucky, Fortran, and all this stuff. But so I'm not suggesting that you take the code, although you're welcome to it. But the models have been selected for particular things that they do as low order models. And I know that other people have other low order model collections like that. So you might want to take a peek at which models we chose to put in when you're thinking about what other models you might want to add next. And I'd be happy to chat more with you about why we pick certain models to put in there.
Okay, thank you. We'll take that in mind. It's also I would like to say that while we do plan on adding some new models to what is right now implemented and some new analysis to what is right now implemented, the idea is that someone who is using the software can understand the abstractions and the interfaces of the models and the analysis that we have built so far, and they can add their own if they feel like it.
Yeah, I get that, and that's a great idea.
Okay. Awesome.
Well, in order to get this thing clear, I have a question. What do you think is different from your own development from the OpenDA framework and from the DART framework? And what would you think that would be the added value of your own tool?
Well, we do have some benefits the way we see it. One of the things is that because it's built right now in Python, it can be set up in another environment that allows for a teacher or a student to not necessarily have a very processing intensive system to run. So it's very, to put it in some way, like open-minded, like someone that maybe doesn't have the best of resources can have their a running start. to put it in a certain way.
Well, thank you very much. Do we have more questions for a student, Andres? No? Okay, so we are going to move forward to the next student, Felipe Acevedo, with his work, First Order Markov Model for Weather Forecast. Go ahead, Felipe. Welcome.
Good afternoon. Thank you very much for the space. My screen. Sorry. Is now sharing? Yes, you can see it?
Yes.
Okay, thank you very much. So, well, I'm going to talk it's a work in progress. First order Markovian model for weather forecast. This work with myself and advised by Professor Elias Niño. Well, as we all know, numerical weather forecasts are of extreme importance in different aspects of life, particularly in scenarios where human life can be compromised, these hurricanes, tsunamis, and so on. Now, numerical models are commonly employed to mimic the behavior of actual system dynamics, for instance, the ocean or the atmospheres. But these models are computationally intensive. High-performance computing is a must to produce forecasts within reasonable computational times, especially for high resolution. So this is what motivates us to look for other approach to have with low computational uh, requirements, high resolution forecast with some quality. For example, for instance, we can think of data-driven models, since now we have decades of meteorological data available. Still, of course, nature is chaotic, and future states may not be represented as some function of the past, unless we have all possible scenarios in our data. So, in this research, we propose a Markovian model with data coming from NOAA's Physical Science Laboratory, reanalysis 2, making use of real observations retrieved from OGMET, made it possible to calculate initial condition that best fits our observation and our data from which start to propagate our linear model. So as I say, this is a Markovian model, and it follows this diagram. We have four observational hours at 0, 6, 12, and 18. And we have where it's the states which live in Rn, where n are the number of variables in our model. We also have the transition matrices from 0, 1, 1, 2, 2, 3, and 3 to 0. This completes a full cycle. And from here is to note that this model is piecewise. Also, these matrices, these transition matrices are given by the solution of this optimization problem, in which we want to minimize the residuals. And there is also the covariance matrix. Now, in order to get our initial condition, we take into account the observations. Mathematically, we know there's a relation. This can be taken into account with the relation given by the Bayes theorem. I think we are all familiar with it. And taking in consider now this cost function, we can now not only minimize the residuals for our model, but also minimize the residual from observation and with our propagation. Though where yk lives in Rm, usually n is less or equal than n, the number of variables in our model, because we won't always have observation for all our variables. So this is for capital N observations. We also have hk, which is a linear observation operator. And of course, we have the data error covariance metrics. So therefore, The initial condition that best fit our observation is given by this optimization problem that can be solved exactly with this expression, where qk is given by the multiplication of our linear observation operator time multiplied k times to our models. Where here is to note that this is not these models are going sequentially. There is k times, but this is a Congress mode 4 because we have observation 4 hours. So we go from M01, 1, 2, 3, 3, 3, 0, so on and so forth. We complete this cycle k mod 4 times. Now this gives us these results. Here we can look at the mean square error, logarithm sense from mean square error for the air temperature since September 1st. From this, we propagate 12 time steps, where in orange, we can see the performance of our model without taking into account observations. And in blue, we can see the performance if we take into account observations. Of course, we can see there is an improvement between these two initial conditions when we propagate, in this case 12 steps times in the future. So then so far the model is capable of making 6-hour forecast for a given variable and making use of the initial condition that best fits our observation, is able to reduce the mean square error with less processing consumption, especially where they are normally distributed. This is what motivates us for a future work to optimally combine with the system dynamics by making use of physical models. We know that a physical model with a low resolution is computationally less intensive, so we can have reasonable computational times. But of course, we want to optimally combine this, its dynamics, with the high resolution of a linear model and also its less computational requirements, so we can have, let's say, the best of both worlds. As well, we want to implement a Gaussian mixture to be able to make the forecast in a more general case and to outperform the current implementations in order to work with more variables at the same time. Currently, the model works with one variable at a time, but the idea is that we can request all the variables we want, and the model can go without any problem. So thank you very much. I'm open to your questions and commentaries.
Well, thank you very much. I invite all the professors to join us for some questions. Professor Anderson, Professor Evanson. Well, I really would love to close this session like summarizing what we did today. I am very pleased and happy that the field of data assimilation is now already part of the Colombian scientific decision making. And we hope that evidence-based decision making will be the part that will make the difference from our country, not only for epidemiological issues, such as the one that Geir already shared with us, but also for different kind of decisions regarding our aerospace, the numerical weather prediction systems, and the pollution and exposure to pollutants of people. I really would love to mention that this kind of techniques have been also widely used by Geir Benson and his team in Norway, and also the team of Professor Hemming in the Netherlands for energy management, reservoir management. Remember that our country also has a lot of possibilities to extract our energy resources from the subsurface. And I really would love to invite all of you to try to think about the use of the observations and the informations that we can obtain from different sources of sensors to acquire it and put into a model in order to forecast. One thing that is very difficult and challenging is getting this kind of developments into an operational way. Yeah, we can have the equations, we can draw the PDFs, we can try to tell a lot about their supercomputing stuff, but getting this into real life is part of the challenges and the opportunities that we as a country are facing. Of course, the seminal works of Geir Benson and Jeff Anderson in different places in the world, they already opened the path, but Elias and me are students and co-researchers, and also the companies in Colombia have the problem of getting this, providing solutions every day. Having a forecast for weather prediction or climate or meteorology or pollution or energy is not easy. We need a lot of power computing, we need a lot of data, we need surface data, we need satellite data, we need vertical profiles, or we need ground data. Minery is one of the main goals for us too, in order to get and extract the information and propagate the information. And nowadays the data assimilation is since the last year that we shared these ideas with the Misión de Sabios for Colombia. And we're trying to put this on top of the tables and get in discussions. Tomorrow we're going to have a very interesting talks from the team from Virginia Tech, led by Professor Sandu, and we also will share the developments of the Colombian Air Force. Having these large-scale models operational at high resolution represents a problem of not only numerical precision, but also scarcity of data. And remember that our country has different regions, and it's not the same having this challenge to reproduce the meteorology here in Medellin or in Barranquilla. Last year, we traveled from Medellin to Barranquilla, and the Professor Benson, Arnold, and Sandu, they experienced how different is the country. And I hope that tomorrow we can realize these challenges, the scientific problems, and the good results that we have been obtaining. And the good thing is that we already have 30 people watching now, and they know that we are doing a good effort in order to get the science part of the mathematical and engineering DNA in Colombia. Thank you very much. I hope to see you tomorrow. Thanks, Professor Anderson. Thanks, Professor Evans. Hemming. Thanks, Professor Sandu, and all the students. Tomorrow, Elias will be sharing, and
Okay. Dr. Anderson, Dr. Benson, Dr. Hemming, and Dr. Sandu, thank you very much for accepting our invitation. And we hope to see you tomorrow during the sessions. It's nice to see you again.
We'll be there.
Take care. Bye-bye.
hope to see you next year here in Colombia.
Yeah, we'll try to arrange that.